In the vast darkness of space, orbits one small world that we call home. But beyond our sun lie trillions of stars, and orbiting those stars are worlds beyond imagination. Some scorching hot, some frozen solid, and even some that might harbor life. Welcome to Stellar Worlds, where we explore some of the most fascinating planets in the universe. Are you ready? Let's begin. For our first world today, let's warp on over to K2-25b, a super-Earth from the K2 mission. 490 light-years from Earth, a planet twice the size of our world orbits a red dwarf star every 3.5 days. It's hot, scorching hot, with temperatures exceeding 1,500 Kelvin. But K2-25b isn't important because it might harbor life. It's important because it sits at a critical boundary in planetary science, a boundary that determines whether worlds end up as rocky super-Earths or gaseous mini-Neptunes. This is K2-25b, a planet teaching us about the forces that shape worlds across our galaxy. A super-Earth discovered by NASA's K2 mission that's helping astronomers understand one of the most important transitions in planetary science, the Arietis Valley, where planets either retain their thick atmospheres or lose them to become rocky worlds. When we discover exoplanets, one of the first questions is, what type of planet is it? Is it rocky like Earth and Mars, gaseous like Jupiter and Saturn, or something in between, a mini-Neptune with a thick hydrogen atmosphere over a rocky core? K2-25b, discovered in 2016, sits right at this critical size range where planets could go either way. At about 2 Earth radii, it's in the zone where some planets are rocky super-Earths while others are gaseous mini-Neptunes. Understanding which type K2-25b is and why helps us understand the processes that determine planetary fates across the galaxy. Today we're going to explore how K2-25b was discovered, what makes its characteristics scientifically valuable, why its position at the Arietis Valley boundary matters, what observations have revealed about its nature, and what future studies might teach us about planetary evolution. Let's dive into the world of super-Earths and the Arietis Valley. Chapter 1. The K2 mission. To understand K2-25b, we first need to understand the mission that discovered it. K2, the ingenious second life of NASA's Kepler Space Telescope. The original Kepler mission launched in March 2009 with one primary goal: stare at a single patch of sky containing about 150,000 stars and search for planets using the transit method. For over 4 years, Kepler was extraordinarily successful, discovering over 2,300 confirmed exoplanets and revolutionizing our understanding of planetary systems. But in May 2013, disaster struck. Kepler relied on 4 reaction wheels, spinning devices that kept the telescope precisely pointed at its target stars. When the second wheel failed, Kepler could no longer maintain the precise pointing needed for its original mission. The mission seemed over. However, the Kepler team refused to give up. They devised an ingenious solution: use pressure from sunlight, solar radiation pressure, as a virtual reaction wheel. By carefully balancing the spacecraft and pointing it along the ecliptic plane, they could maintain enough stability to continue observations. This was the birth of the K2 mission, Kepler's second chance. Instead of staring at one field forever, K2 would observe different fields along the ecliptic for about 80 days each, called campaigns. Between 2014 and 2018, K2 observed 19 campaigns, monitoring over 500,000 stars and discovering hundreds of new planets. K2-25b was discovered during Campaign 2, which observed a region of the sky near the constellation Aquarius from August to November 2014. The mission's ability to observe diverse stellar populations, young stars, old stars, different types of stars, expanded the diversity of exoplanets we could study compared to the original Kepler mission's single field. The K2 mission demonstrated that engineering ingenuity can turn potential failure into continued success. What could have been the end of Kepler became 4 more years of groundbreaking discoveries, including K2-25b. Chapter 2. The Discovery. During K2's Campaign 2, the telescope observed a star catalogued as EPIC 210490365, later designated K2-25. Over the 80-day observation period, K2's sensitive detectors recorded periodic dimming in the star's brightness, the characteristic signature of a transiting planet. The transit signal showed several key features. The dimming occurred every 3.48 days with remarkable regularity. The depth of the dimming was approximately 0.4%, indicating a planet roughly twice Earth size, transiting a small red dwarf star. The transit duration was about 1.5 hours, consistent with a close orbit around a low-mass star. Let me explain how the transit method works, because it's crucial to understanding what we know about K2-25b. When a planet passes in front of its star from our perspective, it blocks a tiny fraction of the starlight. The amount of light blocked depends on the planet's size relative to the star. For K2-25b, which has a radius about 2 times Earth's, orbiting a red dwarf star about 0.3 times the Sun's size, the transit blocks approximately 0.4% of the star's light, a signal clearly detectable with K2's precision photometry. From this transit signal, astronomers can measure several crucial properties. The planet size comes from how much light is blocked. The orbital period comes from how often transits occur. The orbital distance can be calculated from the period using Kepler's laws. And by observing transits at different wavelengths, astronomers can even detect atmospheric signatures. But detecting a transit signal is only the first step. Confirming K2-25b as a genuine planet required follow-up observations from ground-based telescopes. High-resolution imaging verified that K2-25 is a single star with no close companions that could create false positive signals. Spectroscopic observations characterized the host star's properties, its temperature, mass, composition, and age. And radial velocity measurements attempted to detect the gravitational wobble induced by the planet's mass. Though for a planet this small around a faint star, this proved challenging. The radial velocity observations couldn't definitively measure K2-25b's mass due to the faintness of the host star and the small expected signal. However, they could place upper limits, constraining the planet to be less than about 25 Earth masses. Combined with a measured radius of 2.0 Earth radii, this suggested K2-25b is either a rocky super-Earth or a mini-Neptune with a moderate hydrogen-helium atmosphere. K2-25b was announced in 2016 as part of a catalog of K2 planet candidates that were subsequently confirmed through follow-up observations. It immediately attracted attention for its position at the Radius Valley, that critical size range where planetary type becomes ambiguous. Chapter 3. Characteristics of K2-25b. Let's examine K2-25b's characteristics in detail, because they place it at one of the most interesting boundaries in planetary science. K2-25b is classified as a super-Earth, though this classification is somewhat ambiguous at its size. Super-Earths typically refer to planets larger than Earth but smaller than Neptune, roughly in the 1.25 to 2 Earth radii range. At 2.0 Earth radii, K2-25b sits right at the upper edge of what we call a super-Earth, on the boundary with mini-Neptunes. The physical characteristics are as follows. The radius is 2.0 Earth radii, making it exactly twice Earth size. The mass is uncertain. Follow-up observations haven't definitively measured it, but estimates based on composition models suggest it's probably between 6 and 15 Earth masses, depending on whether it's rocky or has a substantial atmosphere. This mass uncertainty is crucial because it determines density, which reveals composition. If K2-25b has a mass around 6 to 8 Earth masses, it would have a density similar to Earth's, suggesting a rocky composition with perhaps a thin atmosphere. If it has a mass around 12 to 15 Earth masses, it would be less dense, suggesting either a water-rich composition or a significant hydrogen-helium atmosphere. The orbital characteristics are well determined from the transit observations. K2-25b orbits its star every 3.4845 days, less than 3.5 Earth days per year. The orbital distance is approximately 0.032 AU, which is about 4.8 million kilometers or 3 million miles. That's extremely close, about 13 times closer than Mercury orbits the Sun. At this distance, K2-25b is certainly tidally locked, with one hemisphere permanently facing the star and the other in eternal darkness. The orbital velocity is approximately 150 kilometers per second, about 335,000 miles per hour, completing its rapid circuit around the small red dwarf. The temperature is estimated at approximately 1,500 to 1,600 Kelvin on the day side, depending on atmospheric properties and heat redistribution. That's about 1,227 to 1,327 degrees Celsius, or 2,240 to 2,420 degrees Fahrenheit. At these temperatures, water would be steam, many rocks would be molten, and any atmosphere would be extremely dynamic. The host star, K2-25, is an M dwarf, a red dwarf star much smaller and cooler than our Sun. It has a mass of approximately 0.29 solar masses, less than one-third the Sun's mass. The radius is about 0.29 solar radii, making it roughly the size of Jupiter. The temperature is approximately 3,450 Kelvin, much cooler than the Sun's 5,778 Kelvin. The age is estimated at several billion years, though precise ages for M dwarfs are notoriously difficult to determine. The distance from Earth is about 490 light-years, placing K2-25b in our cosmic neighborhood, but far enough that detailed observations are challenging. The host star's brightness is magnitude 11.3, too faint for naked eye observation, but accessible to amateur telescopes and professional instruments. Chapter 4. The Radius Valley. What makes K2-25b scientifically fascinating is its position at the Radius Valley, one of the most important discoveries in exoplanet science from the past decade. When astronomers plot all discovered exoplanets by size, a remarkable pattern emerges. There's a noticeable gap in the planet-size distribution around 1.5 to 2.0 Earth radii. Below this gap, roughly 1 to 1.5 Earth radii, we find rocky super-Earths. Above the gap, roughly 2.5 to 4 Earth radii, we find mini-Neptunes with thick hydrogen-helium atmospheres. But right at the gap, the Radius Valley, there are fewer planets than you'd expect. K2-25b, at exactly 2.0 Earth radii, sits right at the upper edge of this valley. The question is it a large rocky super-Earth that barely retained a thin atmosphere, or is it a mini-Neptune with a substantial hydrogen-helium envelope? The Radius Valley is thought to be carved out by photoevaporation, the process where high-energy radiation from the host star strips away planetary atmospheres over time. Here's how it works. When planets form, many acquire substantial hydrogen-helium envelopes from the protoplanetary disk. For planets orbiting close to their stars, intense ultraviolet and X-ray radiation heats the upper atmosphere to extremely high temperatures, 10,000 Kelvin or more. At these temperatures, Atmospheric particles move fast enough to escape the planet's gravity, and the atmosphere gradually evaporates into space. Whether a planet retains its atmosphere depends on several factors: the planet's mass and therefore gravity, the stellar radiation flux, the star's activity level, and the atmosphere's initial mass. Planets above a certain mass threshold can hold onto their atmospheres despite photoevaporation, remaining as mini Neptunes. Planets below the threshold lose their atmospheres, shrinking to become rocky super-Earths. The Arietis Valley represents this transition. K2-25b's position at the boundary makes it a critical test case. If it's rocky, it tells us about the maximum size planets can be while still losing their atmospheres. If it has a substantial atmosphere, it tells us about the minimum mass needed to retain hydrogen-helium envelopes. Red dwarf stars like K2-25 complicate this picture. Young M dwarfs are extremely active, producing frequent powerful flares and intense high-energy radiation. This enhanced activity could strip atmospheres more efficiently, potentially making the Arietis Valley occur at larger sizes around M dwarfs compared to Sun-like stars. Understanding planets like K2-25b helps calibrate our models of photoevaporation and atmospheric evolution. By studying many planets at different sizes around different types of stars at different ages, we build a comprehensive picture of how atmospheres are gained, retained, or lost over billions of years. Chapter 5. Is it habitable? Let's address the habitability question directly. Can K2-25b support life? Almost certainly not. At 1,500 to 1,600 Kelvin surface temperature, K2-25b is far too hot for liquid water. The planet orbits well inside the habitable zone, which for K2-25 would be roughly 0.08 to 0.15 AU. K2-25b, 0.032 AU, is about 2.5 to 5 times closer than the inner edge of the habitable zone. At these temperatures and this proximity to the star, K2-25b faces extreme conditions. The dayside would be heated to rock-melting temperatures. Any water would exist only as steam. The intense stellar radiation would drive vigorous atmospheric escape if an atmosphere exists. Tidal forces would be substantial. Infrequent stellar flares from the active M dwarf would bombard the planet with high-energy particles. But K2-25b's lack of habitability doesn't diminish its scientific importance. Understanding this planet contributes to the broader search for habitable worlds in several ways. First, studying atmospheric retention at the Arietis Valley helps us predict which planets in habitable zones might have atmospheres capable of maintaining surface liquid water. If we understand what determines atmospheric retention for close-in planets like K2-25b, we can apply those lessons to more distant, potentially habitable planets. Second, K2-25b helps us understand M dwarf planetary systems generally. M dwarfs are the most common stars in the galaxy, accounting for about 70% of all stars. If we want to find habitable worlds, we need to understand planets around M dwarfs, including their formation, evolution, and atmosphere properties. Third, every planet we characterize, whether habitable or not, expands our understanding of planetary diversity. Nature creates planets in configurations we never predicted. Each discovery, extreme or typical, habitable or hostile, reveals something about the physical processes operating across the galaxy. K2-25b is a laboratory for studying atmospheric physics, planetary composition, photoevaporation, and the boundary between rocky and gaseous worlds. The knowledge gained from this hot super-Earth ultimately informs the search for temperate, potentially habitable planets. Chapter 6. Atmospheric Research. What do we know about K2-25b's atmosphere? And what are scientists trying to learn? Atmospheric characterization of K2 K2-25b is challenging for several reasons. The host star is relatively faint at magnitude 11.3, providing fewer photons for spectroscopic analysis. The planet is relatively small at 2.0 Earth radii, creating smaller atmospheric signals than larger planets. And the mass uncertainty means we don't know the atmospheric scale height, how quickly density decreases with altitude, which affects how prominent spectral features appear. Despite these challenges, several teams have attempted atmospheric observations of K2-25b using transmission spectroscopy. This technique observes the planet's transit at multiple wavelengths, looking for absorption features caused by atmospheric molecules. The results have been somewhat ambiguous. Some observations suggest the atmosphere might be relatively clear, with some molecular features detectable. Others suggest higher atmospheric opacity, possibly from hazes or clouds that obscure deeper molecular layers. If K2-25b is a mini-Neptune with a hydrogen-helium atmosphere, we'd expect to detect strong spectral features from molecules like water vapor, methane, or other compounds. The hydrogen-dominated atmosphere would have a large scale height due to low molecular weight, making features prominent. If K2-25b is a rocky super-Earth with a thin secondary atmosphere, perhaps outgassed from the interior, the atmosphere would have a much smaller scale height due to higher molecular weight, making features harder to detect. The composition might be dominated by heavier molecules like carbon dioxide, nitrogen, or steam rather than hydrogen and helium. Current observations haven't definitively distinguished between these scenarios, though they've constrained possibilities. The planet likely doesn't have an extremely thick, clear hydrogen atmosphere, as this would produce strong spectral features we haven't seen. But whether it has a moderate hydrogen envelope, a thin hydrogen layer, or no significant atmosphere at all remains uncertain. Additional observations with more sensitive instruments are needed to resolve this question. The atmospheric composition, if determined, would tell us whether K2-25b is truly a super-Earth or a mini-Neptune, directly testing our understanding of the radius valley and photoevaporation. The atmosphere properties also inform us about planetary evolution. If the planet has retained hydrogen-helium, it reveals the conditions under which atmospheres survive intense stellar radiation. If it's lost its primary atmosphere, it shows us photoevaporation in action and helps calibrate models of atmospheric escape. Chapter 7. Scientific Significance. Why does K2-25b matter for planetary science? K2-25b's significance extends across several areas of exoplanet research. Let me highlight the key contributions this planet makes to our understanding. First, radius valley studies. K2-25b sits at the critical boundary between rocky super-Earths and gaseous mini-Neptunes. By determining its composition through mass measurements and atmospheric characterization, we test theories of photoevaporation and atmospheric retention. If many planets at 2.0 Earth radii turn out to be rocky, it suggests photoevaporation is very efficient. If they retain atmospheres, it reveals the conditions enabling atmospheric survival. Second, dwarf planetary systems. K2-25 orbits an M-dwarf, the most common type of star in our galaxy. Understanding planets around M-dwarfs is crucial for assessing the prevalence of habitable worlds. K2-25b helps us understand how planetary systems form and evolve around these low-mass stars, including the effects of stellar activity and flares on atmospheric retention. Third, planetary formation models. The size, orbital distance, and host star properties of K2-25b constrain formation scenarios. Did it form where we find it, or did it migrate inward? Did it start with a massive atmosphere that was partially stripped, or a thin atmosphere that survived? Models that successfully explain K2-25b's properties can be applied to understanding planet formation generally. Fourth, atmospheric evolution pathways. By studying planets at the Arietis Valley, we map out the transition from hydrogen-rich to hydrogen-poor atmospheres. K2-25b represents one snapshot in this transition, showing us an intermediate state between young, envelope-rich planets and ancient, stripped rocky worlds. Fifth, comparative exoplanetology. K2-25b can be compared to other planets in the same size range around different types of stars at different orbital distances. These comparisons reveal which factors most strongly influence planetary properties: stellar type, orbital distance, system age, planetary mass, or other variables. Each of these contributions helps build a comprehensive understanding of how planets form, evolve, and end up with their final properties. K2-25b is one piece of a vast puzzle, but each piece reveals part of the bigger picture. Chapter 8. Future Research. What's next for K2-25b? What can future observations tell us? Several avenues exist for advancing our understanding of K2-25b. The James Webb Space Telescope represents a transformational capability for studying exoplanet atmospheres. JWST's extended wavelength coverage, from 0.6 to 28 microns, allows detection of molecular features that might be invisible to other telescopes. Its sensitivity enables observations of fainter targets and smaller planets than previous instruments could study effectively. For K2-25b, JWST could potentially detect atmospheric molecules definitively, determining whether the planet has a hydrogen-helium envelope or a different atmospheric composition. Observations at multiple wavelengths would constrain cloud properties and atmospheric structure, and repeated observations could search for atmospheric variability or weather patterns. However, K2-25b faces observational challenges even for JWST. The faint host star means fewer photons for spectroscopic analysis. The small planet size means smaller atmospheric signals. And if the atmosphere is heavily clouded or hazy, molecular features might be muted. Whether JWST will observe K2-25b depends on telescope time allocation and scientific priorities. Precise mass measurements would be transformative. If radial velocity observations with next-generation spectrographs could definitively measure K2-25b's mass, we'd know its density and therefore composition. This single measurement would resolve whether it's rocky or has a substantial atmosphere, directly testing Arietis Valley theories. Ground-based, extremely large telescopes coming online in the late 2020s and early 2030s, with 30 to 40-meter primary mirrors, will enable high-resolution spectroscopy that could detect individual molecular absorption lines and measure atmospheric dynamics through Doppler shifts. These capabilities might allow atmospheric characterization even for challenging targets like K2-25b. Long-term monitoring over decades could reveal orbital evolution. Tidal interactions between K2-25b and its star should cause gradual orbital decay, and precise timing of transits over many years could detect this effect, revealing the strength of tidal dissipation. Population studies comparing many planets at the Arietis Valley will ultimately be as valuable as individual detailed characterizations. By observing dozens of planets like K2-25b around different stars, astronomers will identify statistical patterns that individual cases can't reveal. Even without extensive direct observations, K2-25b contributes to these population studies as one example among many, helping define the boundaries of the Arietis Valley and the transition between planetary types. Chapter 9. Conclusion. Let's wrap up by reviewing what makes K2-25b significant for exoplanet science. K2-25b is a super-Earth discovered by NASA's K2 mission during Campaign 2 in 2014, announced in 2016. With a radius of 2.0 Earth radii and an uncertain mass, probably between 6 and 15 Earth masses, it sits at the critical boundary of the Arietis Valley, the gap in planetary size distribution separating rocky super-Earths from gaseous mini-Neptunes. Orbiting an M-dwarf star every 3.48 days at a distance of just 0.032 AU, K2-25b experiences scorching temperatures around 1,500 to 1,600 Kelvin. It's not habitable, far too hot for liquid water, but its scientific value lies in what it teaches us about planetary composition, atmospheric retention, and the processes that determine whether worlds end up rocky or gaseous. The Arietis Valley, carved by photoevaporation, stripping atmospheres from planets unable to hold on to them, represents one of the most important boundaries in planetary science. K2-25b's position at this boundary makes it a critical test case for understanding atmospheric evolution. 490 light-years away, K2-25b continues its rapid orbit, completing a year every 3.5 Earth days. One hemisphere faces an active red dwarf star, heated to rock-melting temperatures. The other knows only darkness, perhaps cooled by atmospheric winds if an atmosphere exists. Is this world rocky, having lost any primordial hydrogen-helium envelope to stellar radiation? Or does it retain a moderate atmosphere, balanced on the edge between super-Earth and mini-Neptune? We don't know for certain yet. But answering this question reveals the forces that shape planets across our galaxy. The story of K2-25b is also the story of the K2 mission, a testament to ingenuity turning potential failure into 4 more years of discoveries. When the Kepler spacecraft's reaction wheels failed, the mission could have ended. Instead, engineers devised a clever solution, and K2 went on to discover hundreds of planets, including K2-25b. Every planet we discover expands our understanding of what's possible. K2-25b, sitting at the Arietis Valley boundary, challenges our models and tests our theories. Whether it ultimately proves to be rocky or gaseous, it will have taught us something fundamental about planetary evolution. For our next world, let's take a deep dive into Mensae C, a super-Earth in a multi-planet system. 60 light-years from Earth, practically in our cosmic backyard, a super-Earth orbits a star visible to the naked eye. This isn't some distant, hypothetical world. Mensae C circles a star you can see from Earth's southern hemisphere without a telescope, completing an orbit every 6 days. It's roughly twice Earth's size, 4 times Earth's mass, and sits in a system with a massive gas giant on a highly eccentric orbit that crosses Mensae C's path every 5 years. This is Mensae C, discovered in 2018 by NASA's TESS mission, proving that remarkable planets orbit some of the nearest and brightest stars in our sky. A super-Earth that's become one of the most interesting nearby exoplanets for several reasons. It orbits a bright, sun-like star that's been studied for decades. It's in a multi-planet system with a giant planet companion, and it's close enough and bright enough that detailed atmospheric studies are actually feasible with current and upcoming telescopes. When astronomers discover exoplanets, proximity matters enormously. A planet 60 light-years away, orbiting a bright star, is far more valuable for detailed study than a planet thousands of light-years away, around a faint star. Mensae C checks all the boxes for being a high-priority target. Nearby, bright host star, interesting properties, and part of a complex planetary system. The Mensae system has actually been known to host planets since 2001, when astronomers discovered Mensae B, a massive gas giant on an extremely eccentric orbit. For 17 years, Mensae B was thought to be alone. But in 2018, NASA's test mission discovered Mensae C transiting the star, revealing that this system hosts not one, but at least two planets, with dramatically different properties and orbital configurations. Today we're going to explore how Mensae C was discovered, what makes its characteristics scientifically valuable, why its position in a multi-planet system with a massive giant planet companion is fascinating, what we know about its potential habitability, what observations have revealed so far, and what future studies might teach us about this nearby super-Earth. Let's discover one of our closest super-Earth neighbors. Chapter 1. The Mensae System. Before diving into Mensae C specifically, we need to understand the system it's part of, because Mensae is one of the nearest multi-planet systems to Earth with dramatically different planet types. Mensae, also cataloged as HD 39091, is a G0V star, essentially a solar twin slightly more massive and luminous than our Sun. It has a mass of 1.09 solar masses, making it about 9% more massive than the Sun. The radius is 1.10 solar radii, so it's about 10% larger. The temperature is approximately 5,980 Kelvin, compared to the Sun's 5,778 Kelvin, slightly hotter, but in the same general class. The age is estimated at around 3.5 to 5.5 billion years, making Mensae slightly younger than our 4.6 billion-year-old Sun, though still a mature main sequence star. The metallicity, the abundance of elements heavier than hydrogen and helium, is slightly supersolar, with about 1.4 times the Sun's metal content. This enhanced metallicity is consistent with the presence of planets, as metal-rich stars are more likely to host planetary systems. What makes Mensae special is its brightness and proximity. At magnitude 5.7, it's just barely visible to the naked eye under dark skies from the southern hemisphere, where it's located in the constellation Mensae. The distance is only 59.7 light-years, close enough that it's among the nearest 100 stars to Earth. This combination of brightness and proximity makes it an exceptional target for detailed observations. The system has two known planets, Mensae B, discovered in 2001, and Mensae C, discovered in 2018. These two planets couldn't be more different. Mensae B is a gas giant with a minimum mass of about 10 Jupiter masses, placing it the boundary between planet and brown dwarf. It orbits on a highly eccentric path with an eccentricity of 0.64, meaning its orbit is significantly elliptical rather than circular. The orbital period is 5.89 years, and the planet's distance from the star varies dramatically, from about 1.3 AU at closest approach to over 6 AU at its farthest. This eccentric orbit suggests a violent dynamical history, possibly involving planet-planet scattering or interactions with a stellar companion. Mensae C, discovered 17 years later, is dramatically different. It's a super-Earth with about 4.8 Earth masses and 2.1 Earth radii, orbiting extremely close to the star at just 0.068 AU with a period of 6.27 days. It orbits on a nearly circular path, in stark contrast to its giant sibling's eccentric orbit. The architecture of the Mensae system, a close-in super-Earth and a distant eccentric giant, raises fascinating questions about formation and dynamical evolution. How did these two very different planets end up in such different orbits? Did they form where we find them, or did they migrate? How have their gravitational interactions shaped the system over billions of years? Understanding Mensae C requires understanding it as part of this larger system, where a massive outer giant may have influenced its formation, migration, or long-term orbital stability. Chapter 2. The Discovery. Mensae C's discovery story actually begins decades before 2018, with the long-term monitoring of Mensae searching for planets. In 2001, astronomers using the Anglo-Australian telescope announced the discovery of Pi Mensae b through radial velocity measurements. The radial velocity method detects planets by observing the gravitational wobble they induce in their host star. As a planet orbits, it pulls the star slightly toward and away from us, creating a Doppler shift in the star's spectrum. For Pi Mensae b, with its massive 10 Jupiter masses and close approaches to the star, the radial velocity signal was substantial, up to 200 meters per second, making it relatively easy to detect with the precision instruments of the early 2000s. The discovery confirmed Pi Mensae hosts at least one planet and established it as a target for continued monitoring. For the next 17 years, astronomers continued observing Pi Mensae with increasingly precise radial velocity spectrographs, gradually refining the orbit of Pi Mensae b and searching for additional planets. These observations would prove crucial for confirming Pi Mensae c. In 2018, NASA's TESS mission, the Transiting Exoplanets Survey satellite, observed Pi Mensae during its survey of the southern sky. TESS is designed to search bright, nearby stars for transiting planets, exactly like Pi Mensae. TESS observed Pi Mensae for 27 days as part of Sector 1 of its survey. During this time, TESS detected periodic dimming in the star's brightness occurring every 6.27 days, with a depth of approximately 0.2%. This transit signal indicated a planet roughly twice Earth size crossing in front of the star. The transit method provides the planet's radius from how much light is blocked and the orbital period from how often transits occur. For Pi Mensae c, the radius measured approximately 2.14 Earth radii, and the orbital period was 6.2681 days, indicating a very close orbit. But detecting a transit signal alone doesn't confirm a planet. There are various false positive scenarios that can mimic transit signals. Confirming Pi Mensae c required combining the TESS data with archival and new radial velocity measurements. This is where the decades of radial velocity monitoring became crucial. Astronomers combined historical radial velocity data from multiple telescopes, including the Anglo-Australian telescope, the HARP spectrograph at La Silla Observatory, and the automated planet finder at Lick Observatory, with new observations targeting the 6.27-day signal. The radial velocity measurements confirmed the planet's existence and measured its mass at approximately 4.82 Earth masses. Combined with a radius of 2.14 Earth radii from TESS, this gives a density of about 4.8 grams per cubic centimeter, suggesting a rocky composition with possibly a thin atmosphere. The discovery was announced in September 2018 in a paper published in the Astrophysical Journal Letters. Pi Mensae c immediately became one of the nearest transiting super-Earths around a bright, sun-like star, making it a high-priority target for atmospheric characterization and detailed study. The discovery also resolved a long-standing question about the Pi Mensae system. For 17 years, astronomers had wondered whether Pi Mensae b was alone or if additional planets existed. The discovery of Pi Mensae c confirmed the system hosts multiple planets, revealing a complex architecture that will help us understand planetary system formation and evolution. Chapter 3. Characteristics of Pi Mensae c. Let's examine Pi Mensae c's characteristics in detail, because they make it one of the most interesting nearby super-Earths. Pi Mensae c is classified as a super-Earth, planets larger than Earth but smaller than Neptune, typically in the range of 1.25 to 2 Earth radii. At 2.14 Earth radii, Pi Mensae c sits at the upper end of the super-Earth range, approaching the size where planets transition from rocky super-Earths to mini-Neptunes with thick hydrogen-helium atmospheres. The physical characteristics are well determined from the combination of transit and radial velocity observations. The radius is 2.14 Earth radii, making it about 114% larger in diameter than Earth, or roughly twice Earth's cross-sectional area. The mass is 4.82 Earth masses, nearly 5 times Earth's mass. The density is 4.8 grams per cubic centimeter, compared to Earth's 5.52 grams per cubic centimeter. This density is crucial for understanding composition. At 4.8 grams per cubic centimeter, Mensae C is denser than a pure water composition, but less dense than pure rock. This suggests it's likely rocky, dominated by iron and silicates like Earth, but possibly with some water content or a thin hydrogen-helium atmosphere. It's definitively not a mini Neptune with a massive hydrogen envelope, as that would produce a much lower density. The surface gravity is approximately 1.3 times Earth's gravity. If you could stand on Mensae C's surface, which you can't, as we'll discuss, you'd weigh about 30% more than on Earth. The orbital characteristics place Mensae C extremely close to its star. The orbital period is 6.2681 days, meaning a year on Mensae C lasts just over 6 Earth days. The semi-major axis, average orbital distance, is 0.0680 AU, which is about 10.2 million kilometers or 6.3 million miles. For perspective, Mercury orbits the Sun at 0.39 AU. Mensae C orbits nearly 6 times closer to its star than Mercury does to ours. At this distance, the planet is certainly tidally locked, with one hemisphere permanently facing the star and the other in eternal darkness. The orbital eccentricity is very low, approximately 0.01, meaning the orbit is nearly circular. This circular orbit contrasts dramatically with the eccentric 0.64 eccentricity of the outer giant Mensae B, suggesting different formation or migration histories. The equilibrium temperature, the temperature the planet would have without an atmosphere or greenhouse effects, is estimated at approximately 1,300 Kelvin, or about 1,027 degrees Celsius, or 1,880 degrees Fahrenheit. This is hot enough that any water would be steam, many metals would be molten, and rocks on the surface would be approaching their melting points. If Mensae C has an atmosphere, greenhouse effects would increase surface temperatures further. Without substantial atmospheric heat redistribution, the permanent day side would be even hotter, while the night side could be somewhat cooler. The host star Mensae, being a Sun-like G0 star, provides relatively stable illumination compared to M dwarfs, which are prone to frequent powerful flares. However, at 0.068 AU, Mensae C receives approximately 900 times more stellar flux than Earth received from the Sun, creating extremely hot conditions despite orbiting a relatively benign star. Chapter 4: Multi-Planet Dynamics. One of the most fascinating aspects of Mensae C is its place in a multi-planet system with a massive giant on an eccentric orbit. The Mensae system's architecture is unusual and scientifically valuable. Let me break down what makes it special. The inner planet, Mensae C, orbits at 0.068 AU every 6.27 days on a nearly circular orbit. The outer planet, Mensae B, orbits with a period of 5.89 years, varying between 1.3 and 6 AU due to its highly eccentric 0.64 eccentricity orbit. The mass ratio between the planets is extreme. Mensae B has roughly 630 times more mass than Mensae C. This architecture raises several questions. First, how stable is the system? Gravitational interactions between planets can destabilize orbits over millions or billions of years. Computer simulations suggest the current configuration is dynamically stable, with Mensae C's close orbit and Mensae B's wide separation preventing strong gravitational perturbations. However, the system likely experienced more complex dynamics in its past. Second, how did this architecture form? The eccentric orbit of Mensae B almost certainly wasn't its original configuration. Gas giants typically form with circular or nearly circular orbits. High eccentricity develops through gravitational interactions, either planet-planet scattering with a third planet that was ejected from the system, or correlative oscillations induced by a distant stellar companion. If planet-planet scattering occurred, it may have affected the entire system, potentially influencing Pi Mensae C's formation location or causing it to migrate inward. Alternatively, Pi Mensae C might have formed after the scattering event in a protoplanetary disk that had already been dynamically processed. Third, does Pi Mensae B's eccentric orbit affect Pi Mensae C? Every 5.89 years, Pi Mensae B approaches the inner system during its periastrum passage. While the planets don't come close enough for strong interactions, subtle gravitational perturbations could potentially affect Pi Mensae C's orbit over long timescales. Precise timing of Pi Mensae C's transits over many years might reveal these perturbations, potentially constraining Pi Mensae B's orbital parameters or revealing additional unseen planets. The multi-planet nature of the Pi Mensae system makes it valuable for comparative studies. Why does the system have one massive giant and one super-Earth, but apparently no intermediate mass planets? What prevented the formation of additional planets? Or were they formed and later removed through dynamical processes? These questions make Pi Mensae C more than just an interesting super-Earth. It's a super-Earth whose properties and evolution are intimately connected to the larger system architecture, providing insights into how complex planetary systems form and evolve. Chapter 5. Habitability Assessment. Let's address the habitability question directly. Can Pi Mensae C support life? Almost certainly not, at least not life as we know it. With an equilibrium temperature around 1,300 Kelvin and receiving 900 times more stellar flux than Earth, Pi Mensae C is far too hot for liquid water on its surface. The planet orbits well inside the habitable zone, which for Pi Mensae would be approximately 0.9 to 1.7 AU. At 0.068 AU, Pi Mensae C is roughly 13 to 25 times closer than the inner edge of the habitable zone. At these temperatures, the surface would be hot enough to glow red from thermal emission. Water exists only as steam. Many rocks would be molten or plastic. The intense stellar radiation drives vigorous atmospheric dynamics if an atmosphere exists. Tidal locking creates extreme temperature contrast between the permanent day side and night side. These conditions are incompatible with life as we understand it. Even extremophile organisms on Earth that survive in hot springs or hydrothermal vents can't tolerate temperatures above about 400 Kelvin. Pi Mensae C's temperatures are 3 times higher. However, Pi Mensae C's uninhabitability doesn't diminish its scientific importance for astrobiology. Understanding this planet contributes to the search for habitable worlds in several ways. First, studying atmospheric retention and composition on planets like Pi Mensae C helps us understand what happens to planets in extreme environments. If Pi Mensae C has retained an atmosphere despite intense stellar irradiation, it reveals the conditions under which atmospheres survive. If it's lost any primordial atmosphere, it demonstrates atmospheric escape processes. Second, understanding super-Earth interiors and compositions informs models of rocky planet formation generally. Pi Mensae C's density of 4.8 grams per cubic centimeter tells us about its bulk composition, likely rocky, with possible water content or a thin atmosphere. This information applies to understanding rocky planets at all orbital distances, including those in habitable zones. Third, Pi Mensae C helps us understand planetary systems around Sun-like stars. Our Sun hosts no super-Earths or mini-Neptunes, the most common planet types in the galaxy. Understanding why super-Earths are common elsewhere but absent from our solar system requires studying systems like Pi Mensae. Fourth, techniques developed for characterizing Mensae C's atmosphere, if it has one, will be applied to potentially habitable planets in the future. Every atmospheric characterization, whether of a hot super-Earth or a temperate Earth-sized world, advances our capabilities and understanding. So while Mensae C itself isn't habitable, studying it contributes essential knowledge to the broader search for life beyond Earth. Chapter 6. Atmospheric Studies. What do we know about Mensae C's atmosphere? And what are scientists trying to learn? Mensae C is an excellent target for atmospheric characterization for several reasons. The host star is bright at magnitude 5.7, providing ample photons for spectroscopic analysis. The planet is relatively large at 2.14 Earth radii, creating larger atmospheric signals than smaller planets. The star is sun-like and relatively quiet, reducing stellar variability that can confound atmospheric measurements. And at only 60 light-years, it's one of the nearest transiting super-Earths around a bright star. Several teams have attempted or planned atmospheric observations of Mensae C using transmission spectroscopy. This technique observes the planet's transit at multiple wavelengths, looking for absorption features caused by atmospheric molecules. Initial observations from ground-based telescopes and the Hubble Space Telescope have searched for atmospheric signatures. The results so far suggest Mensae C likely has some atmosphere, though its exact composition and properties remain uncertain. If Mensae C has a hydrogen-helium-dominated atmosphere, even a relatively thin one, it would create detectable spectral features from molecules like water vapor, methane, and other compounds. The low density compared to pure rock, 4.8 versus 5.5 grams per cubic centimeter, could indicate a hydrogen-helium envelope comprising a few percent of the planet's mass. Alternatively, Mensae C might have a high molecular weight atmosphere composed of heavier molecules like water vapor, carbon dioxide, or nitrogen. Such an atmosphere would have a smaller scale height, the altitude over which atmospheric pressure drops significantly, making spectral features less prominent but still potentially detectable. A third possibility is that Mensae C has lost any primordial hydrogen-helium envelope through photoevaporation and now has either a thin secondary atmosphere outgassed from the interior or no significant atmosphere at all. The intense stellar radiation at 0.068, you could strip atmospheres efficiently, though Mensae C's relatively high mass and gravity might enable atmospheric retention. Distinguishing between these scenarios requires detailed spectroscopic observations, ideally at multiple wavelengths from the optical through the infrared. Such observations would reveal whether water vapor is present and at what abundance, whether molecular hydrogen or helium are detectable, indicating a primordial atmosphere, whether heavier molecules like carbon dioxide or methane are present, whether clouds or hazes obscure deeper atmospheric layers, what the atmospheric temperature structure and circulation patterns are like. These observations would not only characterize Mensae C specifically, but also test theories of atmospheric evolution, photoevaporation, and the transition between rocky super-Earths and mini-Neptunes. Chapter 7. Scientific Significance. Why does Mensae C matter for exoplanet science? Mensae C's scientific importance extends across multiple areas of planetary research. First, it's one of the nearest transiting super-Earths around a bright, sun-like star. The combination of proximity at 60 light-years, a bright magnitude 5.7 host star, and a well-characterized planet makes it one of the best targets for detailed study. There are very few planets closer and brighter that are suitable for atmospheric characterization. Second, it sits at a critical size in the radius distribution. At 2.14 Earth radii, Mensae C is right at the boundary between super-Earths and mini-Neptunes. Understanding its composition, whether it's rocky with a thin atmosphere or has a more substantial hydrogen-helium envelope, directly tests theories about planetary formation and atmospheric retention at this critical size. Third, it's in a multi-planet system with dramatically different planet types. Comparing the super-Earth inner planet with the gas giant outer planet reveals how diverse planetary systems form from the same protoplanetary disk. Why did one region of the disk produce a super-Earth while another produced a giant? What processes led to their very different orbital configurations? Fourth, the eccentric orbit of the outer giant provides a natural laboratory for studying planet-planet interactions and system stability. Long-term transit timing observations of Pi Mensae C could reveal gravitational perturbations from Pi Mensae B, constraining the system's dynamical state and potentially revealing additional unseen planets. Fifth, Pi Mensae C helps build statistics on super-Earth occurrence rates around Sun-like stars. Our solar system lacks super-Earths despite there being the most common planet type around other stars. Understanding this apparent deficit requires characterizing many super-Earths around Sun-like stars like Pi Mensae. Sixth, it's accessible for atmospheric characterization with current and near-future facilities. Unlike more distant or fainter targets that require next-generation telescopes decades away, Pi Mensae C can be studied productively now with instruments like JWST, Hubble, and large ground-based telescopes. Each of these contributions makes Pi Mensae C valuable not just as an individual interesting planet, but as a key piece in understanding planetary diversity, formation, and evolution throughout our galaxy. Chapter 8. Future Research. What's next for Pi Mensae C? What can future observations reveal? Several research directions promise to advance our understanding of Pi Mensae C significantly. The James Webb Space Telescope represents the most powerful tool currently available for characterizing exoplanet atmospheres. JWST's extended wavelength coverage from 0.6 to 28 microns, high sensitivity, and multiple specialized instruments make it ideal for studying planets like Pi Mensae C. For Pi Mensae C, JWST could conduct transmission spectroscopy during transits to measure atmospheric composition, search for molecular features from water, carbon dioxide, methane, and other compounds, constrain atmospheric metallicity and chemistry, characterize cloud and haze properties, and potentially detect thermal emission from the planet's hot day side. Given Pi Mensae's brightness and Pi Mensae C's favorable properties, it's likely to be observed by JWST as part of atmospheric characterization programs. These observations could definitively determine whether the planet has a hydrogen-helium atmosphere, a high molecular weight atmosphere, or has lost its atmosphere entirely. Ground-based, extremely large telescopes currently under construction, the Extremely Large Telescope, the Giant Magellan Telescope, and the 30-meter telescope, will enable high-resolution spectroscopy at optical and near-infrared wavelengths. These facilities could detect individual molecular absorption lines, measure atmospheric dynamics through Doppler shifts, characterize day-night atmospheric differences, and search for atmospheric variability or weather patterns. Long-term transit timing observations over years and decades could reveal dynamical interactions with the outer giant Pi Mensae B. Precise measurements of when transits occur might show timing variations caused by gravitational perturbations, constraining Pi Mensae B's mass and orbit more precisely, or potentially revealing additional unseen planets. Improved radial velocity measurements with next-generation spectrographs might detect additional planets in the system, particularly in the gap between Pi Mensae C at 0.068 AU and Pi Mensae B's closest approach at 1.3 AU. Are there additional planets in this region, or is it empty? Direct imaging of the system, though challenging, might eventually be possible for the outer giant Pi Mensae B. Directly photographing the planet would provide information about its atmosphere, cloud properties, and thermal emission independent of the host star's light. Population studies comparing Mensae C to other super-Earths around Sun-like stars will continue building statistical understanding of this planet class. How common are planets like Mensae C? What determines their properties? How do they fit into the larger picture of planetary diversity? Each of these research directions will contribute to a comprehensive understanding of Mensae C as an individual planet and as representative of an important planetary population around nearby, Sun-like stars. Chapter 9, Conclusion. Let's wrap up by reviewing what makes Mensae C such a significant discovery. Mensae C is a super-Earth discovered by NASA's TESS mission in 2018, orbiting a Sun-like star just 60 light-years from Earth. With 2.14 Earth radii, 4.82 Earth masses, and a density of 4.8 grams per cubic centimeter, it's likely rocky with possibly a thin atmosphere. It orbits extremely close at 0.068 AU every 6.27 days, experiencing temperatures around 1,300 Kelvin. Far too hot for habitability, but perfect for studying super-Earth physics. What makes Mensae C special is its context. It orbits one of the nearest and brightest stars known to host transiting planets, making it accessible for detailed atmospheric studies. It's part of a multi-planet system with a massive gas giant on a highly eccentric orbit, providing insights into system formation and dynamics. It sits at a critical size boundary between super-Earths and mini-Neptunes, testing theories of atmospheric retention and planetary composition. The Mensae system represents the kind of planetary architecture that's common throughout the galaxy, but absent from our solar system. Understanding why super-Earths are everywhere except around our Sun requires studying systems like Mensae. 60 light-years away, a distance light travels in 6 decades, Mensae C continues its rapid orbit. Every 6 days, another year passes on this super-Earth. One hemisphere faces a sun-like star, heated to temperatures where rocks glow. The other knows only starlight and darkness. Is there an atmosphere? If so, what's it made of? How does heat redistribute from day to night? How has the massive outer giant influenced this planet's history? We don't know all the answers yet. But Mensae C is close enough, bright enough, and interesting enough that we can find out. The discovery of Mensae C in 2018 transformed the Mensae system from a single-planet curiosity with an eccentric giant into a complex multi-planet architecture revealing planetary diversity around a nearby solar twin. Every observation of this system, whether characterizing Mensae C's atmosphere, measuring transit timing variations, or studying long-term system stability, adds to our understanding of how planetary systems form and evolve. We live in an era where planets orbiting stars visible to the naked eye can be studied in detail. Mensae, shining at magnitude 5.7 in the southern sky, hosts at least 2 planets we can characterize, model, and understand. That's remarkable. Next, let's head on over to WASP 156b, a hot Jupiter from the WASP survey. 640 light-years from Earth, a gas giant slightly larger than Jupiter circles its star every 4 days. Heated to over 1,600 Kelvin by its nearby sun, WASP 156b represents one of hundreds of hot Jupiters discovered by ground-based telescopes systematically surveying the sky for transiting planets. This is WASP 156b, not the most extreme hot Jupiter, not the largest or the hottest, but precisely because it's representative of the hot Jupiter population, it's scientifically valuable. Every planet we characterize, whether record-breaking or typical, expands our understanding of how gas giants form and evolve across our galaxy. A hot Jupiter discovered in 2018 by the Wide-Angle Search for Planets project that continues the remarkable success of ground-based exoplanet surveys in finding transiting planets around bright stars. The discovery of exoplanets has become almost routine over the past decade. with thousands of planets now cataloged. But each new discovery adds to our statistical understanding of planetary populations, tests our theories of formation and evolution, and expands the diversity of known worlds. WASP 156b might not grab headlines like the most extreme discoveries, but it represents something equally important: a typical hot Jupiter that helps define what these planets are actually like across the galaxy. By studying many hot Jupiters like WASP 156b, planets with moderate temperatures, moderate sizes, typical orbital distances, we build the comprehensive picture needed to understand gas giant physics. Discovered through the transit method by the WASP South facility and confirmed through radial velocity follow-up, WASP 156b orbits a relatively bright star, making it accessible for atmospheric characterization and detailed study. It's one of hundreds of WASP discoveries that have transformed our understanding of planetary systems. Today we're going to explore how the WASP project operates and why it's been so successful, how WASP 156b was discovered and confirmed, what its physical characteristics tell us about hot Jupiter properties, what observations have revealed about its atmosphere, why studying typical hot Jupiters matters for planetary science, and what future observations might teach us. Let's discover what ground-based surveys continue teaching us about exoplanets. Chapter 1. The WASP Project. WASP 156b was discovered by the Wide-Angle Search for Planets, one of the most successful ground-based exoplanet surveys operating today. The WASP project began operations in 2004 with a straightforward but powerful concept: use arrays of small, wide-field cameras to monitor hundreds of thousands of bright stars simultaneously, searching for the periodic dimming that indicates transiting planets. WASP operates from 2 sites to achieve complete coverage of the sky. SuperWASP North operates from La Palma in the Canary Islands, monitoring Northern Hemisphere stars. SuperWASP South operates from the South African Astronomical Observatory, covering Southern Hemisphere stars. Together, these facilities survey essentially the entire sky accessible from Earth. Each WASP facility consists of 8 wide-field cameras using 200mm camera lenses, essentially high-quality telephoto lenses you might find on professional cameras. Each camera covers about 64 square degrees of sky, and together the 8 cameras at each site monitor hundreds of square degrees simultaneously. For perspective, the full moon covers about half a square degree, so each WASP camera observes an area over 128 times larger than the moon's apparent size. The observing strategy is systematic and persistent. Throughout each night, the WASP cameras photograph their target fields repeatedly, building up light curves, plots of brightness versus time, for every star in the field. Automated pipelines analyze these light curves, searching for periodic dimming that could indicate transiting planets. When a promising signal appears, it's flagged for follow-up observations. WASP itself can only detect the transit signal and measure the planet's size and orbital period. Confirming the planet requires additional observations. High-resolution imaging to verify the target is a single star without close companions, spectroscopy to characterize the host star's properties, and radial velocity measurements to confirm the planet's mass. By 2018, when WASP 156b was discovered, the WASP project had already found over 150 exoplanets. The project has been particularly successful at discovering hot Jupiters, large gas giants in very close orbits, because these planets create the largest transit signals and are easiest to detect with WASP's modest precision photometry. WASP's focus on bright stars is strategically important. While space missions like Kepler and TESS can detect smaller planets around fainter stars, ground-based projects like WASP excel at finding planets around bright stars, exactly the targets best suited for detailed atmospheric characterization and follow-up studies. The success of WASP demonstrates that ground-based exoplanet surveys remain essential components of planetary science despite the success of space missions. Different observing strategies complement each other, with ground-based wide-field surveys like WASP identifying bright targets, while space missions discover planets around fainter, more distant stars. Chapter 2. The Discovery. Between 2006 and 2016, WASP South accumulated observations of a star cataloged as 1 SWASP J052743.56-203247.5, later designated WASP 156. The automated pipeline detected periodic transit signals occurring every 3.83 days. The transit signal showed several characteristic features. The dimming occurred every 3.83 days with high regularity, indicating an orbital period of 3.8308 days. The depth of the transit was approximately 1.5%, suggesting a planet roughly the size of Jupiter transiting a Sun-like star. The transit duration was about 3 hours, consistent with a close orbit. And the transit shape, the characteristic U-shaped dimming, matched what you'd expect from a planetary transit rather than other phenomena, like eclipsing binary stars. Let me explain briefly how the transit method works and what it reveals, because understanding this is key to knowing what we've learned about WASP 156b. When a planet passes in front of its star from our perspective, it blocks a fraction of the star's light proportional to the ratio of the planet's cross-sectional area to the stars. For WASP 156b, which has a radius about 1.1 times Jupiter's orbiting a star slightly smaller than the Sun, the transit blocks approximately 1.5% of the star's light, a signal clearly detectable by WASP's cameras. From the transit observations alone, astronomers can measure the planet's radius from the depth of dimming, the orbital period from how frequently transits occur, and the orbital distance can be calculated from the period using Kepler's laws. Additionally, the transit duration and shape provide information about the orbital geometry and stellar properties. However, detecting a transit signal doesn't automatically confirm a planet. Various false positive scenarios can mimic planetary transits, eclipsing binary stars, stars with large spots rotating into view, or background eclipsing binaries blended with the target star's light. Ruling out these alternatives requires follow-up observations. For WASP 156b, confirming the planet required several types of follow-up. High-resolution imaging from larger telescopes verified that WASP 156 is a single star without close companions that could create false signals. Spectroscopic observations characterized the host star, measuring its temperature, mass, radius, composition, and evolutionary state. And radial velocity measurements from precision spectrographs detected the gravitational wobble induced by the planet's mass. The radial velocity observations measured WASP 156b's mass at approximately 0.57 Jupiter masses, about 57% of Jupiter's mass. Combined with the radius of 1.09 Jupiter radii from transits, this gives a density of approximately 0.47 grams per cubic centimeter, less than half Jupiter's density of 1.33 grams per cubic centimeter, indicating moderate inflation. WASP 156b was announced in 2018 in a paper published in the monthly notices of the Royal Astronomical Society, joining the catalog of WASP discoveries. While not the most extreme hot Jupiter in any particular property, it added to the growing statistical sample helping define hot Jupiter characteristics across the galaxy. Chapter 3. Characteristics of WASP 156b. Let's examine WASP 156b's characteristics in detail, because they place it firmly within the typical hot Jupiter population. WASP 156b is classified as a moderately inflated hot Jupiter, a gas giant orbiting very close to its star with elevated temperature and moderate radius expansion from stellar heating. The physical characteristics are well determined from the combination of transit and radial velocity observations. The radius is 1.09 Jupiter radii, making it about 9% larger than Jupiter. The mass is 0.57 Jupiter masses, slightly more than half Jupiter's mass. The density is 0.47 grams per cubic centimeter, placing in the moderately inflated category, denser than extremely puffy hot Jupiters with densities below 0.3 grams per cubic centimeter, but less dense than Jupiter itself. The surface gravity is approximately 0.70 times Jupiter's gravity, meaning objects on WASP 156b would weigh about 30% less than on Jupiter. This relatively weak gravity is a consequence of the planet's lower mass spread over a slightly larger volume. Inside WASP 156b, models predict a structure typical of moderately inflated hot Jupiters, a small rocky or icy core, perhaps 10 to 30 Earth masses, surrounded by layers of metallic hydrogen at extreme pressures, molecular hydrogen in the middle layers, and an extended hot atmosphere heated by the nearby star. The moderate inflation suggests stellar heating is preventing gravitational contraction but isn't causing extreme radius expansion. The orbital characteristics place WASP 156b in the typical range for hot Jupiters. The orbital period is 3.8308 days, less than 4 Earth days per year. The semi-major axis, average orbital distance, is 0.0515 AU, which is about 7.7 million kilometers or 4.8 million miles. For perspective, this is about 7 times closer than Mercury orbits the Sun. At this distance, WASP 156b is certainly tidally locked, with one hemisphere permanently facing the star and the other in eternal darkness. The orbital velocity is approximately 140 kilometers per second, over 300,000 miles per hour, completing its rapid circuit around the star. The orbital eccentricity is very low, essentially zero, meaning the orbit is nearly circular. This circular orbit is typical for close-in planets, as tidal interactions rapidly circularize orbits at these short distances. The equilibrium temperature, the temperature the planet would have without considering atmospheric effects, is estimated at approximately 1,600 to 1,700 Kelvin, or about 1,327 to 1,427 degrees Celsius. This temperature places WASP 156b in a moderately hot range for hot Jupiters, significantly hotter than any planet in our solar system, but not as extreme as ultra-hot Jupiters exceeding 2,500 Kelvin. At these temperatures, atmospheric dynamics are vigorous. Supersonic winds likely race around the planet at several kilometers per second, redistributing heat from the permanent day side to the night side. The day-night temperature difference probably exceeds several hundred Kelvin despite this heat redistribution. Molecules undergo rapid chemical reactions, with some species forming and dissociating continuously depending on local temperature and pressure. The host star, WASP 156, is a G3 dwarf star, similar to our Sun but slightly cooler and less massive. The stellar mass is approximately 0.89 solar masses, about 11% less massive than the Sun. The radius is 0.84 solar radii, making it somewhat smaller. The temperature is approximately 5,700 Kelvin, compared to the Sun's 5,778 Kelvin. The age is estimated at several billion years, indicating a mature main sequence star. The distance from Earth is approximately 640 light-years, placing WASP 156b in a moderately distant range for exoplanets, far enough that detailed observations are challenging but close enough that they're feasible with modern instruments. The host star's brightness is magnitude 11.6, too faint for naked eye observation, but accessible to amateur telescopes and professional instruments. Chapter 4. Atmospheric Studies. WASP 156b's properties make it suitable for atmospheric characterization, though not as ideal as the very brightest and largest targets. Atmospheric studies of exoplanets typically use transmission spectroscopy during transits or emission spectroscopy during eclipses. For WASP 156b, transmission spectroscopy is the more practical approach given current observational capabilities. During a transit, starlight passes through the planet's atmosphere before reaching us. Different molecules in the atmosphere absorb light at characteristic wavelengths, creating spectral signatures that reveal atmospheric composition. The strength of these signals depends on the planet's size, the atmospheric scale height, how quickly atmospheric density decreases with altitude, and the clarity of the atmosphere. For WASP 156b, several teams have attempted or planned atmospheric observations. The moderate size and moderately bright host star make it a reasonable target, though not as high priority as planets around brighter stars or with larger atmospheric signals. Preliminary observations have suggested that WASP 156b likely has a typical hot Jupiter atmosphere dominated by hydrogen and helium, consistent with its classification as a gas giant. Some studies have searched for molecular features from water vapor, sodium, potassium, and other species commonly detected in hot Jupiter atmospheres. The results indicate WASP 156b probably has moderate atmospheric opacity, neither extremely clear, showing strong molecular features, nor heavily clouded, showing completely flat spectra. This moderate opacity could result from high-altitude hazes, patchy cloud coverage, or intrinsic atmosphere properties. At temperatures around 1,600 to 1,700 Kelvin, several atmospheric processes operate. Water vapor should be abundant, but exists in gaseous form at these temperatures. Carbon monoxide and carbon dioxide may be present depending on atmospheric chemistry and metallicity. Alkali metals like sodium and potassium exist in atomic form in the upper atmosphere, creating strong absorption features in optical wavelengths. Cloud formation is possible at these temperatures, though the composition differs from clouds on Earth. Possible cloud materials include silicate condensates, essentially tiny droplets of liquid rock forming on the cooler night side, metal oxides like titanium oxide and aluminum oxide, and possibly sulfur compounds depending on atmospheric composition. The atmospheric dynamics are driven by the intense day-night temperature contrast. Models predict a strong equatorial jet stream racing around the planet at several kilometers per second, high-altitude winds redistributing heat from dayside to nightside, and vigorous vertical convection mixing the atmosphere. These dynamics affect observable atmospheric properties, influencing which molecules are detected and at what abundances. Detailed atmospheric characterization would reveal not just what molecules are present, but also their abundances relative to solar values, the atmospheric metallicity. High metallicity would suggest the planet formed far from the star, where ices were abundant and then migrated inward. Low metallicity would suggest formation closer to the star with less ice incorporation. These compositional clues help reconstruct the planet's formation history. Additionally, atmospheric observations could detect temperature inversions, regions where temperature increases with altitude rather than decreasing. Temperature inversions occur when upper atmospheric compounds absorb stellar radiation efficiently, heating the upper layers. Their presence or absence depends on atmospheric composition and stellar spectrum. While WASP 156b hasn't been as extensively characterized as the brightest hot Jupiter targets, ongoing and future observations continue building understanding of its atmospheric properties and how they compare to other hot Jupiters. Chapter 5. Scientific Significance. What makes WASP 156b scientifically important despite not being an extreme case? WASP 156b's significance lies precisely in its typicality. Understanding planetary populations requires studying both extremes and averages, and WASP 156b represents the average hot Jupiter, moderate in most properties, typical in its characteristics. First, WASP 156b contributes to hot Jupiter population statistics. By characterizing many hot Jupiters across different masses, radii, temperatures, and orbital distances, astronomers identify correlations and patterns. How does inflation correlate with stellar flux? What determines atmospheric opacity? How common are various atmospheric compositions? WASP 156b is one data point among hundreds helping answer these questions. Second, it tests planetary inflation theories. With a density of 0.47 grams per cubic centimeter and moderate radius expansion, WASP 156b sits in the range where theoretical models should reliably predict properties. If models can't explain typical cases like WASP 156b, they need refinement even if they successfully explain extreme cases. Third, WASP 156b helps calibrate atmospheric models. Theoretical predictions for hot Jupiter atmospheres should match observations for typical planets like WASP 156b. Discrepancies between predicted and observed spectra reveal missing physics, unexpected chemistry, surprising cloud behavior, unanticipated circulation patterns. Fourth, it represents the hot Jupiters we'll find around many stars if we look. Extreme planets are rare by definition. If we want to understand what's common versus rare, we need to characterize many typical examples. WASP 156b helps define the norm against which extremes are compared. Fifth, ground-based discoveries like WASP 156b demonstrate the continued value of systematic surveys monitoring bright stars. While space missions discover thousands of planets, ground-based projects identify the brightest targets suitable for detailed follow-up, including atmospheric characterization, which often requires bright host stars. Sixth, WASP 156b contributes to comparative planetology across different stellar types. Its host star is slightly cooler and less massive than the Sun. Does this affect the planet's properties? Comparing hot Jupiters around different spectral types reveals how stellar properties influence planetary characteristics. These contributions make WASP 156b valuable not as a headline-grabbing extreme discovery, but as a reliable representative of the hot Jupiter population, helping build comprehensive understanding of gas giant planets. Chapter 6. Habitability in broader context. Let's address habitability briefly, though the answer for WASP 156b is straightforward. At temperatures around 1,600 to 1,700 Kelvin, WASP 156b is far too hot for life as we know it. Water exists only as steam. Organic molecules would be unstable. The intense radiation would sterilize any surface. And as a gas giant, WASP 156b likely has no solid surface anyway, just increasingly dense layers of hydrogen and helium transitioning to liquid and metallic states at depth. However, studying hot Jupiters like WASP 156b contributes to astrobiology indirectly in several ways. First, understanding gas giant migration helps us understand planetary system architecture. Hot Jupiters like WASP 156b didn't form where we find them. They migrated inward from beyond the snow line. This migration can disrupt interplanetary systems, potentially ejecting smaller rocky planets or altering their orbits. Understanding this process helps predict which systems might harbor stable habitable planets. Second, atmospheric characterization techniques developed for hot Jupiters will eventually be applied to potentially habitable worlds. Every molecule detected, every cloud characterized, every circulation pattern mapped in hot Jupiter atmospheres advances our capability to study more challenging targets, the smaller, cooler, potentially habitable planets. Third, comparing planets across wide ranges of temperature, pressure, and composition reveals fundamental atmospheric physics applicable to all planets. What we learn about chemistry at 1,600 Kelvin on WASP 156b informs models of chemistry at 300 Kelvin on potentially habitable worlds. Fourth, hot Jupiters serve as laboratories for testing theories about planetary formation, migration, and atmospheric evolution. Successfully explaining hot Jupiter properties builds confidence in applying these theories to other planet types. So while WASP 156b itself isn't habitable, and studying it won't directly reveal life elsewhere, the knowledge gained contributes to the broader scientific framework enabling the search for habitable worlds and life beyond Earth. Chapter 7. Future Research. What's next for WASP 156b? What can future observations reveal? Several research directions could advance our understanding of WASP 156b, though it likely won't be the highest priority target for limited telescope time given the existence of brighter and larger planets around brighter stars. The James Webb Space Telescope could potentially observe WASP 156b as part of broader hot Jupiter surveys. JWST's extended wavelength coverage and high sensitivity enable detection of molecular features that might be invisible to other telescopes. For WASP 156b, JWST could definitively detect molecules like water vapor, carbon monoxide, and methane, measure atmospheric metallicity, characterize cloud properties, and constrain temperature structure. Ground-based high-resolution spectroscopy using extremely large telescopes expected in the late 2020s and early 2030s could enable detection of individual molecular absorption lines and measurement of atmospheric dynamics through Doppler shifts. These capabilities might reveal wind speeds at different altitudes, atmospheric rotation patterns, and day-night compositional differences. Long-term transit timing observations over many years could search for additional planets in the system through gravitational perturbations that alter transit timing. Currently, WASP 156 is known to host only one planet, but additional planets might exist at wider separations. Phase curve observations, monitoring the system's total brightness continuously as the planet orbits, could reveal how heat is redistributed across the planet. The brightness should vary as different hemispheres come into view, with the day side appearing brighter than the night side. The amplitude and phase offset of this variation reveal atmospheric circulation efficiency. Continued radial velocity monitoring might detect additional planets through long-term velocity trends or detect the Rossiter-McLaughlin effect during transits, which reveals the angle between the planet's orbital plane and the star's equatorial plane. This spin-orbit alignment provides clues about the planet's migration history. Even without extensive individual observations, WASP 156b contributes to population studies comparing many hot Jupiters to identify trends and test theories statistically. Chapter 8. Conclusion. Let's recap what we've learned about WASP 156b and why it matters. WASP 156b is a moderately inflated hot Jupiter discovered in 2018 by the WASP South facility through the transit method and confirmed via radial velocity measurements. With 1.09 Jupiter radii, 0.57 Jupiter masses, and a density of 0.47 grams per cubic centimeter, it represents a typical hot Jupiter. Moderate inflation, moderate temperature around 1,600 to 1,700 Kelvin, orbiting every 3.83 days at 0.052 AU from a Sun-like star. What makes WASP 156b significant isn't extreme properties, but its representativeness. It's one of many hot Jupiters helping define what these planets are actually like across the galaxy. By studying populations of planets like WASP 156b, astronomers identify patterns and test theories that individual extreme cases can't reveal. The discovery by the WASP project demonstrates the continued importance of ground-based surveys monitoring bright stars for transiting planets. While space missions discover thousands of planets around fainter stars, Ground-based projects identify bright targets suitable for detailed atmospheric characterization. WASP-156b contributes to understanding planetary inflation mechanisms, atmospheric dynamics at high temperatures, gas giant formation and migration, and the diversity of planetary systems. Each characterization, whether of an extreme planet or a typical one, expands our knowledge of how planets form and evolve. 640 light-years away, WASP-156b continues its rapid orbit, completing a year every 3.83 days. One hemisphere faces a sun-like star, heated to temperatures where water is steam and rocks begin to glow. The other knows only darkness, cooled by supersonic winds redistributing heat. Hydrogen and helium dominate the atmosphere, with traces of heavier molecules revealing formation history and chemical processes. This planet won't win records for being the hottest, largest, or most unusual hot Jupiter. But that's not its purpose. WASP-156b matters because it represents what hot Jupiters typically are, not the headlines but the substance, not the extremes but the averages defining the population. Every planet we discover and characterize expands our understanding of planetary diversity. The extremes push our theories to their limits. The averages reveal what's common and what processes operate universally versus what requires special conditions. WASP-156b is one of hundreds of WASP discoveries, each contributing to comprehensive understanding of gas giants, planetary formation, atmospheric physics, and the incredible variety of worlds filling our galaxy. For our next planet today, let's dive into K2-196b, a super-Earth from the K2 mission. In 2013, when NASA's Kepler Space Telescope lost its second reaction wheel, the mission seemed over. 4 years of groundbreaking discoveries, thousands of planets found, and suddenly dead in space. But engineers refused to give up. They devised an ingenious solution using sunlight itself as a stabilizer, giving Kepler a second life as the K2 mission. Between 2014 and 2018, this resurrected spacecraft discovered hundreds more planets, including K2-196b, a super-Earth twice the size of our world, orbiting a star 900 light-years away every 9 days. This planet sits right at the boundary between rocky super-Earths and gaseous mini-Neptunes, making it crucial for understanding how planets transition between these two very different types. This is the story of K2-196b, a planet that exists because engineers turned failure into triumph. A super-Earth discovered in 2018 by NASA's K2 mission that sits at one of the most important boundaries in planetary science, the Arietis Valley, where planets either retain thick atmospheres to become mini-Neptunes or lose them to become rocky super-Earths. When we study exoplanets, size matters tremendously for determining what type of world we're looking at. Planets around 1 to 1.5 Earth radii are almost certainly rocky. Planets above 2.5 Earth radii likely have thick hydrogen-helium atmospheres. But right in between, at roughly 1.5 to 2.5 Earth radii, there's a transition zone where planets could go either way. K2-196b, with a radius around 2 Earth radii, sits right in this critical range. Understanding whether it's a large rocky planet or a small gaseous one tells us about atmospheric retention, planetary formation, and the processes that determine planetary fates across billions of years. The K2 mission that discovered K2-196b represents one of the great success stories in space exploration, a mission that refused to die, engineers who found creative solutions, and a spacecraft that continued making discoveries long after it should have been declared lost. Today we're going to explore how the K2 mission came to be and why it succeeded, how K2-196b was discovered, and what makes it scientifically interesting, what its characteristics tell us about the super-Earth population, why its position at the Arietis Valley matters, what we know about potential habitability, and what future observations might reveal. Let's discover a super-Earth born from engineering ingenuity. Chapter 1. The Discovery. During K2's Campaign 5, from April to July 2015, the spacecraft observed a star cataloged as EPIC 2124-28863, later designated K2-196. Over the 80-day observation period, K2's sensitive detectors recorded periodic dimming in the star's brightness, occurring every 9.2 days. The dimming was subtle, only about 0.3%, but clearly detectable with K2's precision photometry. The transit duration was roughly 2.5 hours, and the shape matched what you'd expect from a planetary transit. Let me explain how the transit method works and what it reveals, because this is fundamental to understanding what we know about K2-196b. When a planet passes in front of its star from our perspective, it blocks a tiny fraction of the starlight. The amount blocked depends on the planet's size relative to the star. For K2-196b, with a radius about 2 times Earth's orbiting a star smaller than the Sun, the transit blocks approximately 0.3% of the star's light, a subtle signal requiring precise measurements. From transit observations, astronomers can determine several key properties. The planet's size comes from how much light is blocked. The orbital period comes from how frequently transits occur. The orbital distance can be calculated from the period using Kepler's laws. And by observing transits at different wavelengths, astronomers can potentially detect atmospheric signatures. But K2 could only measure these properties. Confirming K2-196b as a genuine planet and determining its mass required follow-up observations from ground-based telescopes. The Discovery team used several validation techniques. Statistical validation examined the probability that the signal came from a planet versus false positive scenarios like eclipsing binary stars or background objects. High-resolution imaging from ground-based telescopes checked for nearby companion stars that could create false signals. And attempts were made to measure the planet's mass through radial velocity observations. Though for a planet this small around a relatively faint star, precise mass measurements proved challenging. Based on the validation process, K2-196b was confirmed as a genuine planet. The radius was determined to be approximately 2.0 Earth radii, exactly twice Earth size. The mass, while uncertain due to difficulties in radial velocity measurements, was estimated from statistical relationships between mass and radius for planets of this size, suggesting roughly 5 to 8 Earth masses depending on composition. K2-196b was announced in 2018 as part of a catalog of K2 discoveries. It immediately attracted attention for its position right at the Radius Valley, that critical size boundary separating rocky super-Earths from gaseous mini-Neptunes. The discovery added to K2's impressive legacy of finding planets across diverse environments and demonstrated that even a compromised spacecraft could continue making scientifically valuable discoveries. Chapter 2. Characteristics of K2-196b. Let's examine K2-196b's characteristics in detail, because they place it at one of the most scientifically interesting boundaries in planetary science. K2-196b is classified as a super-Earth, though this classification becomes ambiguous at its size. Super-Earths typically refer to planets between 1.25 and 2 Earth radii, larger than Earth but smaller than Neptune. At exactly 2.0 Earth radii, K2-196b sits at the upper edge of what we'd call a super-Earth, right at the boundary with mini-Neptunes. The physical characteristics are reasonably well determined from K2 observations. The radius is 2.0 Earth radii, making it precisely twice Earth's diameter. The mass is uncertain. Radial velocity measurements haven't definitively constrained it, but statistical relationships and composition models suggest approximately 5 to 8 Earth masses, depending on whether the planet is rocky or has a substantial atmosphere. This mass uncertainty is crucial because it determines density, which reveals composition. If K2-196b has a mass around 5 to 6 Earth masses, it would have a density around 4 to 5 grams per cubic centimeter, suggesting rocky composition possibly with a water-rich layer or thin atmosphere. If it has a mass around 7 to 8 Earth masses, the lower density would suggest either significant water content or a hydrogen-helium envelope. The orbital characteristics are well determined from K2's transit observations. K2-196b orbits its star every 9.204 days, just over 9 Earth days per year. The semi-major axis is approximately 0.08 AU, which is about 12 million kilometers or 7.5 million miles. That's extremely close, roughly 5 times closer than Mercury orbits the Sun. At this distance, K2-196b is certainly tidally locked, with one hemisphere permanently facing the star and the other in perpetual darkness. The orbital velocity is approximately 100 kilometers per second, completing its rapid circuit around the small M-dwarf star. The equilibrium temperature, the temperature without considering atmospheric effects, is estimated at approximately 700 to 800 Kelvin, or about 400 to 500 degrees Celsius. This is significantly hotter than Earth, but cooler than many hot Jupiters, placing K2-196b in the warm super-Earth category. At these temperatures, liquid water couldn't exist on the surface, it would be steam. However, the temperatures aren't so extreme that all volatiles would be lost. If K2-196b has an atmosphere, it could retain water vapor, carbon dioxide, and other molecules. The host star, K2-196, is an M-dwarf, a red dwarf star much smaller and cooler than our Sun. The stellar mass is approximately 0.4 solar masses, less than half the Sun's mass. The radius is about 0.4 solar radii, making it roughly 40% the Sun's diameter. The temperature is approximately 3,600 Kelvin, much cooler than the Sun's 5,778 Kelvin. The age is estimated at several billion years, making K2-196 a mature M-dwarf. M-dwarfs live for trillions of years, so even old M-dwarfs are still on the main sequence. The metallicity, abundance of elements heavier than hydrogen and helium, appears to be roughly solar, though precise measurements for faint M-dwarfs are challenging. The distance from Earth is approximately 900 light-years, placing K2-196b in a moderately distant range for exoplanets. Far enough that detailed observations are challenging, but close enough that they're potentially feasible with advanced instruments. Chapter 3. The Arietis Valley. What makes K2-196b scientifically fascinating is its position at the Arietis Valley, one of the most important discoveries in exoplanet science. When astronomers plot all discovered exoplanets by size, a remarkable pattern emerges. There's a noticeable gap in the planet size distribution around 1.5 to 2.0 Earth radii. Below this gap, we find rocky super-Earths. Above it, we find mini-Neptunes with thick hydrogen-helium atmospheres. But right at the gap, the Arietis Valley, there are fewer planets than statistical models would predict. K2-196b, at exactly 2.0 Earth radii, sits right at the upper edge of this valley. The question is it a large rocky super-Earth that lost any primordial hydrogen-helium envelope, or is it a small mini-Neptune that retained a substantial atmosphere? The Arietis Valley is thought to be carved by photoevaporation, the process where high-energy radiation from the host star strips away planetary atmospheres over time. Here's how it works. When planets form, many acquire hydrogen-helium envelopes from the protoplanetary disk. For planets orbiting close to their stars, intense ultraviolet and X-ray radiation heats the upper atmosphere to extremely high temperatures. At these temperatures, atmospheric particles can escape the planet's gravity, and the atmosphere gradually evaporates into space. Whether a planet retains its atmosphere depends on several factors: the planet's mass and gravity, the intensity of stellar radiation, the star's activity level and age, and the initial atmospheric mass. Planets above a certain mass threshold can hold onto their atmospheres despite photoevaporation, remaining as mini Neptunes. Planets below the threshold lose their atmospheres, shrinking to become rocky super-Earths. The Radius Valley represents this transition. K2-196b's position at the boundary makes it a critical test case for understanding atmospheric retention and loss. M-dwarf stars like K2-196 complicate this picture. Young M-dwarfs are extremely active, producing frequent powerful flares and intense high-energy radiation for billions of years. This enhanced and prolonged activity could strip atmospheres more efficiently than around Sun-like stars, potentially affecting where the Radius Valley occurs. Understanding planets like K2-196b helps calibrate photoevaporation models and tests our understanding of atmospheric evolution. By studying many planets at different sizes around different types of stars at different ages, we build a comprehensive picture of how atmospheres are gained, retained, or lost. Determining K2-196b's composition through precise mass measurements or atmospheric characterization would directly test these theories. If it's rocky, it demonstrates that photoevaporation can remove atmospheres from planets up to 2 Earth radii around M-dwarfs. If it has a substantial atmosphere, it reveals the conditions enabling atmospheric survival despite intense stellar radiation. Chapter 4. Habitability Assessment. Let's address habitability directly. Could K2-196b support life? Almost certainly not, at least not life as we know it. With equilibrium temperatures around 700 to 800 Kelvin, K2-196b is far too hot for liquid water on its surface. The planet orbits well inside the habitable zone, which for K2-196 would be roughly 0.15 to 0.3 AU. At 0.08 AU, K2-196b is about twice as close as the inner edge of the habitable zone. At these temperatures, any water would exist only as steam. The surface, if rocky, would be heated to temperatures where many minerals are unstable. The intense stellar radiation drives vigorous atmospheric dynamics if an atmosphere exists, and frequent stellar flares from the active M-dwarf would bombard the planet with high-energy particles. Tidal locking creates additional challenges. The permanent day side would be even hotter than the equilibrium temperature suggests, while the night side would be much cooler. Without substantial atmospheric circulation to redistribute heat, temperature extremes would be severe. However, K2-196b's lack of surface habitability doesn't diminish its astrobiological importance. Understanding this planet contributes to the search for habitable worlds in several ways. First, studying atmospheric retention at the Radius Valley helps predict which planets in habitable zones might maintain atmospheres capable of supporting liquid water. The lessons learned from close-in planets like K2-196b apply to understanding more distant, potentially habitable planets. Second, K2-196b helps us understand M-dwarf planetary systems generally. M-dwarfs are the most common stars in the galaxy, about 70% of all stars. If we want to find habitable worlds, we need to understand planets around M-dwarfs, including their formation, atmospheric properties, and response to stellar activity. Third, every characterized planet expands our understanding of planetary diversity. K2-196b reveals physical processes operating under conditions we can't replicate on Earth. Atmospheric physics at 700 Kelvin, photoevaporation under intense M-dwarf radiation, planetary composition at the super-Earth to mini-Neptune boundary. Fourth, techniques developed for characterizing K2-196b's atmosphere, if successfully implemented, will eventually be applied to potentially habitable planets. Every atmospheric observation advances our capabilities for studying more challenging targets. So while K2-196b itself isn't habitable, studying it contributes essential knowledge to the comprehensive framework enabling the search for life beyond Earth. Chapter 5: Atmospheric Research. What do we know about K2-196b's atmosphere? And what are scientists trying to learn? Atmospheric characterization of K2-196b is challenging for several reasons. The host star is relatively faint at magnitude 12.6, providing fewer photons for spectroscopic analysis. The planet is moderately sized at 2 Earth radii, creating smaller atmospheric signals than larger planets. The mass uncertainty means we don't know the atmospheric scale height precisely, affecting how prominent spectral features appear. Despite these challenges, K2-196b is potentially accessible for atmospheric studies, particularly with next-generation facilities. The planet's position at the Arietis Valley makes atmospheric characterization especially valuable. Determining composition would directly test theories about atmospheric retention and loss. If K2-196b is a mini-Neptune with a hydrogen-helium atmosphere, we'd expect strong spectral features for molecules like water vapor, methane, and other compounds. The hydrogen-dominated atmosphere would have a large scale height due to low molecular weight, making features prominent. If K2-196b is a rocky super-Earth with a thin secondary atmosphere, perhaps outgassed from the interior, the atmosphere would have a much smaller scale height due to higher molecular weight. The composition might be dominated by heavier molecules like water vapor, carbon dioxide, or nitrogen rather than hydrogen and helium. Current observational capabilities haven't definitively characterized K2-196b's atmosphere. Future observations with more sensitive instruments are needed to resolve whether the planet has retained hydrogen-helium or lost it to photoevaporation. The James Webb Space Telescope could potentially observe K2-196b, though it likely won't be the highest priority target given the existence of larger planets around brighter stars. However, if observed, JWST could detect molecular features, constrain atmospheric metallicity, characterize cloud properties, and determine whether the planet has hydrogen-helium or a heavier atmosphere. Ground-based, extremely large telescopes coming online in the late 2020s might enable high-resolution spectroscopy, detecting individual molecular lines and measuring atmospheric dynamics. These observations could reveal which side of the Arietis Valley K2-196b occupies, large rocky planet or small mini-Neptune. Chapter 6: Scientific Significance. Why does K2-196b matter for exoplanet science? K2-196b's significance extends across several research areas. Let me highlight the key contributions. First, Arietis Valley studies. K2-196b sits at the critical boundary separating rocky super-Earths from gaseous mini-Neptunes. Determining its composition through mass measurements or atmospheric characterization directly tests photoevaporation theories and reveals the conditions enabling atmospheric retention versus loss. Second, M-dwarf planetary systems. K2-196 orbits an M-dwarf, the most common stellar type. Understanding planets around M-dwarfs is crucial for assessing the prevalence of habitable worlds. K2-196b helps us understand how planetary systems form and evolve around low-mass stars, including effects of prolonged stellar activity on atmospheric retention. Third, K2 mission legacy. K2-196b represents the scientific value extracted from a mission that should have ended but continued through engineering ingenuity. Every K2 discovery demonstrates that creative solutions can extend missions beyond designed lifetimes. Fourth, super-Earth population statistics. By characterizing many planets like K2-196b at the Arietis Valley boundary around M dwarfs, we build statistical understanding of what determines planetary outcomes. How common are planets of this size? What fraction retain atmospheres versus losing them? Fifth, atmospheric evolution pathways. K2-196b represents a snapshot in planetary evolution, either a planet that lost its atmosphere or one that retained it. Understanding, which reveals the timescales and efficiency of photoevaporation around M dwarfs. These contributions make K2-196b valuable for understanding planetary formation, atmospheric physics, and the diversity of worlds filling our galaxy. Chapter 7. Future Research. What's next for K2-196b? What can future observations reveal? Several research directions could advance our understanding significantly. Precise mass measurements would be transformative. If radial velocity observations with next-generation spectrographs could definitively measure K2-196b's mass, we'd know its density and composition. This single measurement would resolve whether it's rocky or has a substantial atmosphere. JWST observations, while not guaranteed, could potentially characterize the atmosphere if the planet is selected for observation programs. JWST could detect molecules, measure atmospheric metallicity, and determine atmospheric type, hydrogen-helium versus heavier composition. Ground-based, extremely large telescopes in the late 2020s and early 2030s will enable high-resolution spectroscopy, potentially revealing atmospheric composition and dynamics, even for challenging targets like K2-196b. Long-term transit timing observations might reveal additional planets in the system through gravitational perturbations. Currently, K2-196 is known to host only one planet, but others might exist. Population studies comparing many planets at the Arietis Valley will ultimately be as valuable as individual detailed characterizations. By observing dozens of planets like K2-196b around different stars, astronomers identify statistical patterns revealing underlying physical processes. Chapter 8. Conclusion. Let's recap what makes K2-196b significant. K2-196b is a super-Earth discovered by NASA's K2 mission during Campaign 5 in 2015, announced in 2018. With a radius of 2.0 Earth radii and an estimated mass of 5 to 8 Earth masses, it sits at the Arietis Valley boundary, the critical transition between rocky super-Earths and gaseous mini-Neptunes. Orbiting an M-dwarf star every 9.2 days at 0.08 AU, the planet experiences temperatures around 700 to 800 Kelvin, too hot for surface habitability, but ideal for studying atmospheric retention and super-Earth physics. What makes K2-196b special is its position at a scientific boundary. Determining whether it's rocky or has a substantial atmosphere directly tests photoevaporation theories and reveals planetary evolution around M dwarfs, the most common stars in our galaxy. The discovery by K2 reminds us that some of the greatest achievements come from refusing to accept defeat. When Kepler lost its reaction wheels in 2013, the mission could have ended. Instead, engineers found a creative solution, and K2 went on to discover hundreds more planets, including K2-196b. 900 light-years away, K2-196b continues its rapid orbit, completing a year every 9 days. One hemisphere faces a small red dwarf star, heated to temperatures where water is steam. The other knows only starlight and darkness. Is this world rocky, having lost any primordial hydrogen-helium envelope to stellar radiation? Or does it retain a moderate atmosphere, balanced at the edge between super-Earth and mini-Neptune? We don't know for certain yet. But answering this question reveals fundamental processes shaping planets throughout the galaxy. The story of K2-196b is really two stories: a planet at a critical scientific boundary, and a mission that refused to die. Both teach us that limitations can become opportunities, that boundaries reveal the most interesting physics, and that persistence yields discoveries. If your head is often up in the clouds, you're going to love this next planet. WASP-61b, a hot Jupiter with cloudy skies. 750 light-years from Earth, a gas giant slightly larger than Jupiter orbits its star every 3.9 days. Heated to nearly 1500 Kelvin by its nearby sun, WASP-61b represents one of the most studied hot Jupiters for atmospheric characterization. And what astronomers have discovered challenges our assumptions about exoplanet atmospheres. This world has cloudy skies that hide molecular features, teaching us that atmospheric opacity is more common and complex than we initially thought. This is WASP-61b, a planet revealing that most hot Jupiters don't have the clear, cloudless atmospheres we once expected, but instead hide their secrets behind high-altitude hazes and clouds. A hot Jupiter discovered in 2012 that has become one of the key planets helping astronomers understand atmospheric clouds and hazes on exoplanets, a phenomenon that's proven far more common than initial theoretical models predicted. When scientists first began studying hot Jupiter atmospheres, many expected to see strong molecular absorption features, clear spectral signatures from water vapor, sodium, methane, and other molecules. The high temperatures and vigorous mixing should create relatively clear atmospheres, where molecules are easily detectable. But observations of many hot Jupiters, including WASP-61b, revealed something different. Muted or absent spectral features suggesting high-altitude clouds or hazes blocking our view of the deeper atmosphere. This discovery forced a fundamental rethinking of hot Jupiter atmospheric physics. WASP-61b has been observed multiple times by the Hubble Space Telescope in ground-based facilities specifically to characterize its atmosphere and understand what creates these cloudy conditions. The results contribute to a growing understanding that atmospheric opacity, whether from clouds, hazes, or other aerosols, is the norm rather than the exception among hot Jupiters. Discovered by the WASP South facility through the transit method and confirmed via radial velocity measurements, WASP-61b orbits a relatively bright star, making it accessible for the detailed atmospheric studies that have revealed its cloudy nature. Today we're going to explore how the WASP project operates and its success in finding transiting planets, how WASP-61b was discovered and confirmed, what its physical characteristics tell us about moderately inflated hot Jupiters, what atmospheric observations have revealed about its cloudy skies, why understanding atmospheric clouds matters for exoplanet science, and what future observations might teach us. Let's explore a world where clouds hide atmospheric secrets. Chapter 1. The WASP Project. WASP-61b was discovered by the Wide-Angle Search for Planets, one of the most successful ground-based exoplanet surveys. The WASP project, which we've discussed in previous videos, operates two facilities providing complete sky coverage. SuperWASP North at La Palma in the Canary Islands monitors Northern Hemisphere stars, while SuperWASP South at the South African Astronomical Observatory covers the southern sky. Together, they've discovered over 200 exoplanets since beginning operations in 2004. Each WASP facility uses 8 wide-field cameras with 200mm lenses, monitoring hundreds of square degrees of sky simultaneously. This enormous coverage allows WASP to observe hundreds of thousands of stars each night, building up light curves that reveal transiting planets. The observing strategy is systematic and persistent. Night after night, year after year, WASP photographs the same fields, searching for the periodic dimming that indicates a planet crossing in front of its star. When promising signals appear, they're flagged for follow-up observations to confirm the planet and characterize its properties. WASPs focus on relatively bright stars, typically magnitude 8 to 12, is strategically important. While these bright targets represent only a small fraction of all stars, they're precisely the objects best suited for detailed atmospheric characterization. Ground-based spectroscopy and space telescope observations both benefit enormously from bright host stars that provide more photons for analysis. This strategy has proven remarkably successful. Many of the hot Jupiters with the best characterized atmospheres were discovered by WASP, including WASP 61b. By finding planets around bright stars, WASP identifies the targets that can be studied in detail with follow-up observations. By 2012, when WASP 61b was discovered, the project had already found dozens of hot Jupiters and was well established as a leading planet discovery program. The continued success of WASP demonstrates that ground-based wide-field surveys remain essential components of exoplanet science, complementing space missions by identifying bright targets for detailed study. Chapter 2. The Discovery. Between 2006 and 2011, WASP South accumulated observations of star cataloged as 1SWASP J045601.36-3936.7, later designated WASP 61. The automated pipeline detected periodic transit signals occurring every 3.876 days. The transit depth was approximately 1.2%, indicating a planet roughly Jupiter-sized, transiting a Sun-like star. The transit duration was about 3 hours, and the shape was consistent with a genuine planetary transit. From these transit observations, astronomers could immediately estimate several properties. The planet's radius, determined from how much light was blocked, was approximately 1.2 Jupiter radii. The orbital period of 3.876 days indicated a very close orbit, and the transit timing precision suggested the orbit was likely circular, as tidal forces rapidly circularize orbits at such short distances. However, confirming WASP 61b required follow-up observations beyond the WASP survey data. Several types of observations were necessary to validate the planet and determine its complete properties. High-resolution imaging from larger telescopes verified that WASP 61 is a single star without close companions that could create false positive transit signals. This step is crucial because various scenarios involving binary stars can mimic planetary transits. Spectroscopic observations characterized the host star, measuring its temperature, surface gravity, metallicity, and other properties needed to accurately determine the planetary parameters. Understanding the star precisely is essential for accurately measuring the planet. Radial velocity measurements from precision spectrographs detected the gravitational wobble induced by the planet's mass. These observations measured WASP 61b's mass at approximately 2.06 Jupiter masses, roughly twice Jupiter's mass. Combined with a radius of 1.24 Jupiter radii from transits, this gives a density of approximately 1.1 grams per cubic centimeter. This density, slightly less than Jupiter's 1.33 grams per cubic centimeter, indicates moderate inflation. WASP 61b is expanded by stellar heating, but not extremely so. It sits in the middle of the hot Jupiter density distribution, neither extremely puffy nor unusually compact. WASP 61b was announced in 2012 in a paper published in Astronomy and Astrophysics. The discovery added to WASP's growing catalog of well-characterized transiting planets around relatively bright stars. What made WASP 61b particularly valuable wasn't extreme properties, but its suitability for atmospheric characterization. The bright host star at magnitude 11.8, the large planetary radius, and the frequent transits every 3.9 days made it an excellent target for detailed atmospheric studies. Chapter 3. Characteristics of WASP 61b. Let's examine WASP 61b's characteristics in detail. WASP 61b is classified as a moderately inflated hot Jupiter, a gas giant in a very close orbit with moderate radius expansion from stellar heating. The physical characteristics are well determined from combined transit and radial velocity observations. The radius is 1.24 Jupiter radii, making it about 24% larger in diameter than Jupiter. The mass is 2.06 Jupiter masses, roughly twice Jupiter's mass. The density is 1.1 grams per cubic centimeter, indicating moderate inflation, expanded beyond Jupiter's density, but not extremely so. The surface gravity is approximately 2.1 times Jupiter's gravity. This relatively strong gravity compared to more inflated hot Jupiter's affects atmospheric properties. Stronger gravity creates a smaller atmospheric scale height, making atmospheric features less prominent in spectroscopic observations. Inside WASP 61b, models predict a structure typical of hot Jupiters: a rocky or icy core, perhaps 10 to 20 Earth masses, surrounded by layers of metallic hydrogen at extreme pressures, molecular hydrogen in the middle regions, and an extended hot atmosphere. The moderate inflation suggests stellar heating is preventing gravitational contraction but not causing extreme radius expansion. The orbital characteristics place WASP 61b firmly in the hot Jupiter category. The orbital period is 3.876 days, less than 4 Earth days per year. The semi-major axis is 0.0516 AU, approximately 7.7 million kilometers. For perspective, this is about 7 times closer than Mercury orbits the Sun. At this distance, WASP 61b is certainly tidally locked with one hemisphere permanently facing the star. The orbital velocity is approximately 140 kilometers per second, over 300,000 miles per hour. The orbital eccentricity is very low, essentially zero, meaning the orbit is circular. This is typical for close-in planets where tidal forces rapidly circularize initially eccentric orbits. The equilibrium temperature is estimated at 1400 to 1500 Kelvin, or about 1100 to 1200 degrees Celsius. This places WASP 61b in a moderately hot range for hot Jupiters, significantly hotter than any solar system planet, but cooler than ultra-hot Jupiters exceeding 2500 Kelvin. At these temperatures, atmospheric dynamics are vigorous. Supersonic winds likely race around the planet at several kilometers per second, redistributing heat from the permanent day side to the night side. The day-night temperature difference probably exceeds several hundred Kelvin despite this heat transport. The host star, WASP 61, is an F7 star, slightly hotter and more massive than our Sun. The stellar mass is approximately 1.2 solar masses. The radius is 1.3 solar radii, making it about 30% larger than the Sun. The temperature is approximately 6,200 Kelvin, compared to the Sun's 5,778 Kelvin. The age is estimated at several billion years, indicating a mature main-sequence star. The metallicity is approximately solar, meaning the star has similar abundances of heavy elements as our Sun. The distance from Earth is approximately 750 light-years, placing WASP 61b in a moderately distant range for exoplanets. The host star's brightness at magnitude 11.8 makes it accessible for detailed spectroscopic observations, though not as ideal as the very brightest targets. Chapter 4. The Cloudy Atmosphere. What makes WASP-61b particularly scientifically interesting is what atmospheric observations have revealed, or more accurately, what they haven't revealed. WASP-61b has been observed multiple times specifically to characterize its atmosphere through transmission spectroscopy. This technique observes the planet's transit at multiple wavelengths, looking for absorption features caused by atmospheric molecules. When starlight passes through the planet's atmosphere during transit, different molecules absorb light at characteristic wavelengths. Water vapor absorbs strongly in the near-infrared. Sodium creates distinctive absorption features in the optical. Methane, carbon monoxide, and other molecules each have unique spectral signatures. For a hot Jupiter at 1400 to 1500 Kelvin with a hydrogen-helium-dominated atmosphere, theoretical models predicted strong, easily detectable molecular features. The high temperatures should prevent widespread cloud formation, creating clear atmospheres where molecules are readily observable. But when astronomers observed WASP-61b's transmission spectrum using the Hubble Space Telescope in ground-based facilities, they found something different: a relatively flat spectrum with muted or absent molecular features. A flat transmission spectrum typically indicates high-altitude clouds or hazes blocking our view of the deeper atmosphere where molecular absorption occurs. Instead of seeing through multiple atmospheric layers and detecting molecules at various altitudes, we see only the top of an opaque cloud deck. This discovery was initially surprising, but has proven to be common. Many hot Jupiters show evidence for atmospheric opacity obscuring molecular features. WASP-61b is one of many examples teaching us that cloudy or hazy atmospheres are the norm rather than clear skies. What creates these clouds at such high temperatures? At 1400 to 1500 Kelvin, most familiar cloud materials like water ice or even water droplets can't exist. The clouds on WASP-61b must be composed of materials that remain condensed at extreme temperatures. Possible cloud materials include silicate condensates, essentially tiny droplets of liquid rock composed of magnesium and iron silicates, metal oxides like titanium oxide and aluminum oxide, sulfur compounds depending on atmospheric chemistry, and photochemically produced hazes created when ultraviolet radiation breaks apart molecules and creates complex organic compounds. The exact composition of WASP-61b's clouds remains uncertain, but their presence is clear from the muted spectral features. Understanding what creates these clouds and under what conditions they form is crucial for predicting which planets will have clear versus cloudy atmospheres. The atmospheric dynamics also play a role. WASP-61b's moderate surface gravity creates a relatively small atmospheric scale height compared to more inflated hot Jupiters. This makes atmospheric features less prominent even without clouds. Adding clouds further mutes the signals. Some observations have detected weak features potentially attributable to specific molecules, suggesting the clouds aren't completely opaque at all wavelengths. Patchy cloud coverage, with clear regions and cloudy regions, could allow some molecular detection while still obscuring most features. The presence of clouds has important implications for understanding WASP-61b's energy balance and climate. Clouds affect how much stellar radiation is absorbed versus reflected, influencing the day-night temperature contrast and atmospheric circulation patterns. High-altitude clouds could also affect atmospheric chemistry by shielding lower layers from ultraviolet radiation. Chapter 5. Scientific Significance. Why does WASP-61b matter for exoplanet science? WASP-61b's significance extends beyond being another hot Jupiter discovery. Its cloudy atmosphere makes it valuable for understanding a phenomenon that's proven more common and complex than initially expected. First, WASP-61b contributes to understanding atmospheric cloud prevalence. Early theoretical models suggested most hot Jupiters would have relatively clear atmospheres, where molecular features are easily detected. Observations of WASP-61b and many other hot Jupiters reveal this isn't true. Atmospheric opacity is common, forcing revision of atmospheric models. Second, it helps identify what determines atmospheric opacity. By comparing many hot Jupiters with varying cloud coverage, from clear to completely opaque, astronomers identify patterns. Does cloud coverage correlate with temperature, surface gravity, atmospheric metallicity, or stellar properties? WASP-61b is one data point in building these statistical relationships. Third, WASP-61b demonstrates the challenges of atmospheric characterization. Even for favorable targets, bright host stars, large planetary radii, frequent transits, clouds can obscure the atmospheric features we're trying to detect. Understanding this limitation is essential for planning observations and interpreting results. Fourth, it tests atmospheric models that must now include cloud physics. Theoretical models that successfully predict which planets have clouds versus clear skies, what materials form clouds at different temperatures, and how clouds affect observability can be trusted for making predictions about planets we haven't yet characterized. Fifth, WASP-61b reveals the diversity of hot Jupiter atmospheres. Not all hot Jupiters are the same. They have different temperatures, gravities, atmospheric compositions, and cloud properties. Understanding this diversity reveals the range of processes operating in gas giant atmospheres. Sixth, observations of WASP-61b help develop techniques for seeing through or around clouds. Can observations at longer wavelengths penetrate clouds? Do temporal variations in cloud coverage create opportunities for detecting molecules? These techniques will be essential for characterizing cloudy atmospheres on other planets. Chapter 6. Habitability and Broader Context. Let's briefly address habitability, though for WASP-61b the answer is straightforward. At temperatures around 1400 to 1500 Kelvin, WASP-61b is far too hot for life as we know it. Water exists only as steam. Organic molecules are unstable. The intense radiation would sterilize any surface. And as a gas giant, WASP-61b has no solid surface anyway. However, studying hot Jupiters like WASP-61b contributes to astrobiology in indirect but important ways. First, understanding atmospheric clouds on hot Jupiters informs predictions about clouds on potentially habitable planets. If we can predict which planets have clouds based on temperature, pressure, and composition, we can better interpret observations of cooler, potentially habitable worlds where clouds might obscure biosignatures. Second, techniques developed for characterizing cloudy hot Jupiter atmospheres will eventually be applied to smaller, cooler planets. Every successful detection through clouds, every method for constraining cloud properties, every model improvement advances our capabilities for studying more challenging targets. Third, hot Jupiters serve as laboratories for understanding atmospheric physics under extreme conditions. The lessons learned about cloud formation, atmospheric circulation, and radiative transfer at 1400 Kelvin in 4 models of atmospheres at all temperatures. Fourth, understanding why clouds form on some hot Jupiters but not others reveals fundamental atmospheric physics applicable to any planet with an atmosphere. So while WASP-61b itself isn't habitable, studying its cloudy atmosphere contributes essential knowledge to the framework enabling searches for life beyond Earth. Chapter 7. Future Research. What's next for WASP-61b? What can future observations reveal? Several research directions could advance our understanding of WASP-61b's atmosphere and resolve the mysteries of its cloudy skies. The James Webb Space Telescope represents the most powerful tool currently available for characterizing exoplanet atmospheres. JWST's extended wavelength coverage from 0.6 to 28 microns provides opportunities to observe wavelengths where clouds might be more transparent. Longer infrared wavelengths often penetrate clouds better than visible or near-infrared light. For WASP-61b, JWST could potentially detect molecular features at wavelengths where cloud opacity is lower, constrain cloud properties by measuring which wavelengths are affected versus which remain clear, characterize thermal emission from the planet's hot day side, and search for atmospheric variability that might indicate temporal changes in cloud coverage. Ground-based high-resolution spectroscopy using extremely large telescopes expected in the late 2020s could enable detection of individual molecular absorption lines, even through clouds. These observations might reveal atmospheric composition and dynamics despite the presence of clouds. Phase curve observations, monitoring the system's brightness continuously as the planet orbits, could reveal how heat is redistributed across the planet and how cloud coverage affects the day-night temperature contrast. Variations in brightness as different hemispheres come into view reveal circulation patterns and thermal structure. Long-term monitoring over many years might detect atmospheric variability. Do clouds come and go? Are there weather patterns creating temporal changes in the transmission spectrum? Detecting such variability would reveal atmospheric dynamics operating on observable timescales. Comparative studies observing many hot Jupiters with similar properties to WASP-61b will identify which factors most strongly influence cloud coverage. By building statistics across many planets, patterns emerge that individual observations can't reveal. Even if WASP-61b isn't extensively observed by every new facility, it contributes to our understanding as one example among many cloudy hot Jupiters, helping define the population and test theories. Chapter 8. Conclusion. Let's recap what makes WASP-61b significant. WASP-61b is a moderately inflated hot Jupiter discovered in 2012 by the WASP South facility. With 1.24 Jupiter radii, 2.06 Jupiter masses, and a density of 1.1 grams per cubic centimeter, it represents a typical moderately inflated hot Jupiter orbiting every 3.9 days at 0.05 AU. What makes WASP-61b scientifically important is its cloudy atmosphere. Observations by Hubble Space Telescope and ground-based facilities revealed muted spectral features indicating high-altitude clouds or hazes obscuring molecular absorption. This discovery, shared by many hot Jupiters, forced astronomers to recognize that atmospheric opacity is far more common than early models predicted. The clouds on WASP-61b, composed of high-temperature materials like silicates or metal oxides, teach us about atmospheric physics under extreme conditions. Understanding what creates these clouds, when they form, and how they affect observations is essential for characterizing exoplanet atmospheres generally. WASP-61b demonstrates both the opportunities and challenges of atmospheric characterization. Even favorable targets can have clouds obscuring the features we want to detect. Developing techniques to see through clouds or constrain cloud properties despite limited spectral information is crucial for advancing atmospheric science. 750 light-years away, WASP-61b continues its rapid orbit, completing a year every 3.9 days. One hemisphere faces a star slightly hotter than our Sun, heated to temperatures where rocks become vapor. The other knows only darkness and stellar winds. And throughout its atmosphere, clouds form, high-altitude aerosols of materials that would be solid minerals on Earth, but exist as vapor and tiny droplets at 1400 Kelvin. These clouds hide the planet's secrets, obscuring the molecular features astronomers want to detect. But even clouds teach us something. They reveal that hot Jupiter atmospheres are more complex than simple models predicted. They show us that opacity is common, that atmospheric physics operates differently than we initially thought, and that each planet has its own atmospheric fingerprint determined by temperature, gravity, composition, and dynamics. The story of WASP 61b is the story of learning that nature is more complex than our models. We expected clear skies revealing molecular abundances. We found clouds hiding atmospheric secrets. This forced us to develop better models, new observing techniques, and deeper understanding. Every cloudy atmosphere we characterize brings us closer to predicting which planets will have clear versus cloudy skies. Every technique we develop for seeing through clouds advances our capability to study atmospheres generally. And every planet like WASP 61b teaches us that the universe is full of surprises. Our last world today is truly a special one. 30 Arietis b, a gas giant in a quadruple star system. 136 light-years from Earth, a gas giant nearly 10 times Jupiter's mass orbits an aging star that's already begun its evolution off the main sequence. Discovered in 2009 through the patient observation of stellar wobbles, 30 Arietis b orbits every 335 days at a distance where Earth would be temperate, but with 10 Jupiter masses, this world is anything but Earth-like. This is 30 Arietis b, a planet orbiting a star you can see with the naked eye, discovered through the radial velocity method that launched the exoplanet revolution, and teaching us about planetary systems around evolved stars that are beginning their transition toward becoming red giants. We're exploring 30 Arietis b, a massive gas giant discovered in 2009 that orbits an evolved star visible to the naked eye. This planet represents several fascinating aspects of exoplanet science. Planets around evolved stars, the radial velocity detection method that pioneered exoplanet discoveries, and massive planets orbiting at distances similar to Earth's orbit around the Sun. When we think about exoplanets, we often focus on those around main sequence stars like our Sun, stable, middle-aged stars burning hydrogen in their cores. But stars don't stay on the main sequence forever. Eventually, they exhaust their core hydrogen, expand into subgiants, and eventually red giants, and fundamentally change the environments experienced by any orbiting planets. 30 Arietis b orbits just such a star, one that's already left the main sequence and begun evolving toward becoming a red giant. This evolution has implications for the planet's environment, history, and future fate. As the star expands, overcoming millions of years, will 30 Arietis be engulfed? How has the planet's orbit changed as the star evolved? These questions make planets around evolved stars scientifically fascinating. The planet was discovered using the radial velocity method, the technique that found the first confirmed exoplanet around a Sun-like star in 1995 and has since discovered hundreds more. By detecting the gravitational wobble a planet induces in its star, astronomers can determine the planet's mass and orbital properties even without directly seeing the planet. And remarkably, 30 Arietis itself is visible to the naked eye under dark skies at magnitude 5.7. You can look up at the constellation Aries and see the star hosting this massive gas giant, connecting you directly to a planetary system over 100 light-years away. Today we're going to explore how 30 Arietis b was discovered through stellar wobbles, what its characteristics tell us about massive gas giants, why planets around evolved stars matter for understanding planetary system evolution, what we know about the 30 Arietis system's architecture, how evolved stellar hosts affect planetary environments, and what future observations might reveal. Let's discover a massive world orbiting an aging star. Chapter 1. The Radial Velocity Method. To understand 30 Arietis b's discovery, we need to understand the radial velocity method that detected it. The radial velocity method, also called the Doppler spectroscopy method, detects planets by observing the gravitational wobble they induce in their host stars. When a planet orbits a star, it's not quite accurate to say the planet orbits the star. Rather, both planet and star orbit their common center of mass, called the barycenter. For a massive planet, the barycenter is displaced noticeably from the star's center, causing the star to move in a small orbit as the planet moves in its large orbit. From Earth's perspective, this stellar motion has a component toward and away from us. The star moves slightly toward us during part of the orbit and slightly away during another part. This motion creates a Doppler shift in the star's spectral lines, the characteristic wavelengths where elements absorb light in the star spectrum. When the star moves toward us, these lines shift toward blue wavelengths, blue shifted. When the star moves away, they shift toward red wavelengths, red shifted. By measuring these shifts with extreme precision, astronomers can detect stellar velocities as small as 1 meter per second, slower than walking pace. The amplitude of the radial velocity signal depends on the planet's mass and orbital distance. More massive planets create larger wobbles. Closer orbiting planets create faster wobbles because orbital speeds increase closer to the star. The orbital period is directly measured from how long the wobble cycle takes to repeat. 430 Arietis b, with nearly 10 Jupiter masses orbiting at 1 astronomical unit. The radial velocity signal is substantial, over 100 meters per second. This large amplitude made 30 Arietis be relatively easy to detect once sufficient observations accumulated. The radial velocity method has strengths and limitations. It's excellent at detecting massive planets, especially those in close or moderate orbits. It can detect planets we can't see directly. It provides the planet's mass and orbital parameters precisely, and it works for any stellar orientation, unlike the transit method, which requires specific geometry. However, the method has limitations. It only measures the minimum mass. The true mass depends on the orbital inclination, which radial velocity alone can't determine. It's biased toward massive planets in close orbits because they create the strongest signals, and it requires many observations over time, making it resource-intensive for long-period planets. 430 Arietis b, discovered through radial velocity observations. We know the planet's minimum mass is 9.88 Jupiter masses. The true mass could be higher depending on orbital inclination, but for typical random orbital orientations, the minimum mass is usually close to the actual mass. The radial velocity method launched the exoplanet revolution when it discovered 51 Pegasi b in 1995, the first confirmed exoplanet around a sun-like star. Since then, it's discovered hundreds of planets and remains a crucial technique complementing transit surveys and direct imaging programs. Chapter 2. The Discovery. 30 Arietis b was discovered through a long-term radial velocity monitoring program observing evolved stars. Between approximately 2003 and 2008, astronomers using precision spectrographs at several observatories monitored 30 Arietis for radial velocity variations. These observations accumulated measurements showing a periodic wobble with an amplitude exceeding 100 meters per second, a strong signal indicating a massive planetary companion. The observations revealed several key properties. The orbital period was approximately 335 days, just under 1 Earth year. The velocity amplitude of over 100 meters per second indicated a very massive companion, and the shape of the radial velocity curve suggested a moderately eccentric orbit rather than a circular one. From these observations, astronomers calculated the planetary parameters. The minimum mass was 9.88 Jupiter masses, nearly 10 times Jupiter's mass. The semi-major axis was 1.3 astronomical units, about 30% farther than Earth orbits the Sun. The orbital eccentricity was 0.289, indicating a moderately elliptical orbit. The discovery was announced in 2009 in a paper published in the Astrophysical Journal. The planet was designated 30 Arietis B following the standard nomenclature, where the star is 30 Arietis and planets are designated with lowercase letters starting with B. What made this discovery particularly interesting was the evolved nature of the host star. 30 Arietis is a K1 subgiant, a star that has exhausted its core hydrogen and begun evolving off the main sequence. The star has expanded to about 7 times its original main sequence radius and increased in luminosity. This evolution has implications for the planet's current environment and future fate. The discovery team noted that 30 Arietis B adds to the growing catalog of planets around evolved stars. Studying these systems reveals how planetary systems change as their host stars evolve, how planetary orbits may migrate outward due to stellar mass loss, and what happens to planets as their stars become red giants and eventually white dwarfs. Follow-up observations continued refining the orbital parameters and searching for additional planets in the system. Long-term monitoring remains valuable for detecting long-period companions, improving orbital constraints, and measuring any secular changes in the system over time. The detection of 30 Arietis B demonstrates the power of patient, long-term radial velocity monitoring. Detecting a planet with a 1-year orbital period requires observations spanning multiple years to confirm the periodic signal and distinguish it from stellar activity or instrumental effects. Chapter 3. Characteristics of 30 Arietis B. Let's examine 30 Arietis B's characteristics in detail, because they place it in an interesting parameter space of massive gas giants. 30 Arietis B is classified as a massive gas giant or potentially a brown dwarf, depending on how you define the boundary. With a minimum mass of 9.88 Jupiter masses, it sits well above typical hot Jupiters, but below the deuterium burning limit at roughly 13 Jupiter masses that traditionally defines the planet brown dwarf boundary. However, the true mass depends on orbital inclination. If the orbit is viewed edge-on from Earth, the minimum mass equals the true mass. If the orbit is viewed at an angle, the true mass is higher. For a random orbital orientation, there's about an 86% probability the true mass is less than twice the minimum mass, meaning 30 Arietis B's true mass likely ranges from 10 to 20 Jupiter masses. This mass makes 30 Arietis B one of the most massive exoplanets known. Most detected exoplanets have masses between 1/10 and 5 Jupiter masses. Planets exceeding 10 Jupiter masses are relatively rare, making 30 Arietis B exceptional in mass even among gas giants. The radius is unknown because 30 Arietis B doesn't transit. The orbital geometry doesn't align for transits to be visible from Earth. However, theoretical models predict gas giants this massive have radii similar to Jupiter despite being 10 times more massive. The additional mass causes stronger gravitational compression, preventing significant radius expansion. So 30 Arietis B likely has a radius around 1 to 1.2 Jupiter radii. The density would therefore be very high compared to typical hot Jupiters, perhaps 8 to 12 grams per cubic centimeter compared to Jupiter's 1.33. This high density reflects the exotic interior structure of massive gas giants, with extreme pressures creating metallic hydrogen and possibly even solid hydrogen at the core. The orbital characteristics are well determined from radial velocity observations. The orbital period is 335 days, remarkably close to Earth's 365-day year. The semi-major axis is 1.3 astronomical units, about 30% farther than Earth's 1 AU. The orbital eccentricity is 0.289, indicating a moderately elliptical orbit. This eccentricity means the orbital distance varies significantly during each orbit. At periastron, closest approach, 30 Arietis B is about 0.93 AU from the star. At apastron, farthest distance, it's about 1.67 AU. This variation is proportionally larger than Mercury's eccentric orbit and affects the stellar flux received at different orbital phases. The equilibrium temperature depends on orbital position and atmosphere properties. At periastron, receiving more stellar flux, the temperature might reach 350 to 400 Kelvin. At apastron, receiving less flux, it might cool to 250 to 300 Kelvin. These are rough estimates, but indicate 30 Arietis b is relatively cool for a gas giant. Much cooler than hot Jupiter's, but warmer than Jupiter's 165 Kelvin. The host star 30 Arietis is a K2-15 subgiant. The spectral type, K1, indicates it's cooler than the Sun, but hotter than typical red dwarfs. The luminosity class 4 indicates it's a subgiant, evolved off the main sequence, but not yet a red giant. The stellar mass is approximately 1.27 solar masses, slightly more massive than the Sun. The radius is about 7 solar radii, 7 times the Sun's radius, indicating significant expansion from the main sequence size. The temperature is approximately 5,000 Kelvin, cooler than the Sun's 5,778 Kelvin. The age is estimated at several billion years, with the star having already spent its main sequence lifetime and begun evolution. The metallicity appears roughly solar or slightly enhanced. The distance from Earth is approximately 136 light-years, relatively nearby in galactic terms. And remarkably, 30 Arietis is visible to the naked eye at magnitude 5.7 under dark skies. This makes it one of the few naked-eye stars known to host planets, connecting amateur and professional astronomy in a tangible way. Chapter 4. Evolved Stellar Hosts. What makes 30 Arietis be particularly interesting is its evolved stellar host and the implications for planetary system evolution. When stars like the Sun exhaust their core hydrogen, they begin significant changes. The core contracts and heats up, causing the outer envelope to expand dramatically. The star increases in luminosity and radius, transitioning from a main sequence dwarf to a subgiant and eventually to a red giant. This evolution fundamentally changes the environment experienced by any orbiting planets. For 30 Arietis, this evolution is underway. The star has expanded from a main sequence radius around 1 solar radius to its current 7 solar radii, a 7-fold expansion. The luminosity has increased correspondingly, though exact values depend on evolutionary models. And this evolution will continue over the next several 100 million years, with the star eventually becoming a full red giant, potentially 100 times its original size. These changes have several implications for 30 Arietis b. First, the increased stellar luminosity means the planet receives more radiation than it did when the star was on the main sequence. This increased heating affects atmospheric temperature and chemistry. Second, the stellar wind, the stream of charged particles flowing from the star, increases in strength as stars evolve, potentially affecting atmospheric retention. Third, stellar mass loss during evolution causes orbits to expand slightly as the star's gravitational pull weakens. Additionally, as 30 Arietis continues evolving, the habitable zone moves outward. When the star was on the main sequence, the habitable zone was closer, perhaps at 0.5 to 1.5 AU. Now, with increased luminosity, the habitable zone might extend from 1 to 2 AU or beyond. In the distant future, when 30 Arietis becomes a red giant, the habitable zone could extend to 5 AU or farther. However, for 30 Arietis b specifically, habitability isn't relevant. At nearly 10 Jupiter masses, it's a gas giant without a solid surface. But hypothetical moons of 30 Arietis b might benefit from the evolving habitable zone, though whether large moons could remain stable around such a massive planet in a moderately eccentric orbit is unclear. Another question concerns planetary migration during stellar evolution. Does the planet's orbit change as the star loses mass and expands? Theoretical models predict slight outward migration due to mass loss, but observational confirmation is difficult without decades or centuries of monitoring. Planets around evolved stars also inform us about the future of our own solar system. In about 5 billion years, the Sun will evolve off the main sequence, expand into a red giant, and potentially engulf Mercury, Venus, and possibly Earth. Studying planets around evolved stars today reveals what planetary systems look like billions of years into stellar evolution. Additionally, finding massive planets around evolved stars tells us about planet formation efficiency around more massive stars. 30 Arietis at 1.27 solar masses was slightly more massive than the Sun when it formed. The presence of a nearly 10 Jupiter-mass planet suggests that slightly more massive stars can form very massive planetary companions, consistent with the observation that planet occurrence rates increase with stellar mass for intermediate mass stars. The moderate orbital eccentricity of 0.289 is also interesting. Hot Jupiters typically have circular orbits due to tidal circularization, but at 1.3 AU, tidal forces are much weaker. The eccentricity might be primordial, left over from planet-planet scattering or other dynamical processes during system formation, or it could have been amplified during stellar evolution. Chapter 5. Atmospheric Considerations. What can we say about 30 Arietis B's atmosphere despite not having direct observations? Since 30 Arietis B doesn't transit and is too faint to image directly, we have no direct atmospheric observations. However, theoretical models and comparisons to similar objects allow informed speculation about atmospheric properties. At nearly 10 Jupiter masses and temperatures ranging from 250 to 400 Kelvin, depending on orbital position, 30 Arietis B's atmosphere is certainly dominated by hydrogen and helium. The planet's strong gravity prevents these light gases from escaping, maintaining a hydrogen-rich primordial atmosphere. At these temperatures, water, methane, and ammonia would exist in various phases depending on altitude and local conditions. Methane is particularly interesting. At the cooler temperatures during a pastron, methane could condense into clouds, creating dynamic atmospheric conditions that change with orbital position. Ammonia might also condense in the upper atmosphere, forming cloud layers similar to those on Jupiter and Saturn. The high mass and strong gravity create a very compact atmosphere with a small scale height, the altitude over which atmospheric pressure drops significantly. This compact atmosphere would make spectroscopic detection challenging even if observations were attempted, as atmospheric features would be relatively muted compared to lower mass planets with larger scale heights. The moderate orbital eccentricity creates interesting atmospheric dynamics. As the planet moves from a pastron to periastron, stellar heating increases substantially, potentially driving vigorous atmospheric circulation. The temperature difference between a pastron and periastron might create seasonal effects analogous to Earth seasons, but driven by changing stellar distance rather than axial tilt. Deep in the atmosphere, at millions of times atmospheric pressure on Earth, hydrogen transitions to an exotic metallic state, metallic hydrogen, that conducts electricity like metal. This metallic hydrogen layer likely generates a powerful magnetic field through dynamo processes, potentially creating auroras and protecting any hypothetical moons from stellar radiation. While we can't observe 30 Arietis B's atmosphere directly, future observations might be possible if advanced techniques develop. High-contrast imaging from extremely large telescopes might eventually resolve the planet as a point of light separate from the star, enabling spectroscopic characterization. Or long-duration observations might detect reflected starlight as the planet orbits, revealing atmospheric properties through phase curves. Chapter 6. Scientific Significance. Why does 30 Arietis b matter for exoplanet science? 30 Arietis b contributes to several research areas. First, understanding massive planets near the planet-brown dwarf boundary. At 9.8 Jupiter masses minimum, 30 Arietis b sits in a mass range where the distinction between planets and brown dwarfs becomes ambiguous. Studying such objects reveals the continuum between planetary and substellar objects and tests formation theories in this intermediate mass range. Second, planets around evolved stars. As stars evolve off the main sequence, they change dramatically, affecting their planetary systems. 30 Arietis b provides one example of a planetary system undergoing stellar evolution, helping us understand how planets respond to changing stellar environments and what happens to planetary systems over billions of years. Third, massive planets at moderate orbital distances. Most detected exoplanets are either close-in hot Jupiters or distant giants detected by direct imaging. 30 Arietis b at 1.3 AU fills an important parameter space between these extremes, revealing planet populations at intermediate separations. Fourth, planets around slightly more massive stars. 30 Arietis was more massive than the Sun when it formed, and the presence of such a massive planet informs us about planet formation efficiency as a function of stellar mass. Metal-rich and slightly more massive stars appear to form massive planets more readily than Sun-like stars. Fifth, orbital dynamics and eccentricity. The moderate eccentricity of 30 Arietis b's orbit raises questions about its origin and evolution. Understanding what creates and maintains eccentric orbits at these distances tests theories of planet-planet scattering, secular perturbations, and dynamical evolution during stellar evolution. These contributions make 30 Arietis b valuable despite lacking atmospheric observations or transit measurements. Every characterized exoplanet expands our understanding of planetary diversity and the physical processes creating that diversity. Chapter 7. Habitability Context. Let's briefly address habitability, though for 30 Arietis b the answer is straightforward. As a gas giant with nearly 10 Jupiter masses, 30 Arietis b has no solid surface and cannot support life as we know it. The planet is primarily hydrogen and helium compressed to exotic states in the interior, with no stable surface on which life could exist. However, hypothetical large moons orbiting 30 Arietis b are an interesting consideration. If such moons existed and were massive enough to retain atmospheres, they might orbit within the gradually expanding habitable zone as 30 Arietis evolves. The changing habitable zone boundaries during stellar evolution create a moving target for habitability. But large moons could potentially experience habitable conditions temporarily during the star's subgiant or early red giant phases. The challenge is whether large moons could remain stable around such a massive planet in a moderately eccentric orbit. Tidal forces from both planet and star might destabilize moon orbits over time. Additionally, the planet's orbit carries it from 0.93 to 1.67 AU, sometimes inside and sometimes outside any fixed habitable zone boundaries. More broadly, studying planets like 30 Arietis b around evolved stars informs our understanding of how habitable zone boundaries change over stellar lifetimes and what happens to planets during stellar evolution. Knowledge applicable to predicting the far future fate of potentially habitable worlds around other stars. Chapter 8. Future Research. What's next for 30 Arietis b? What could future observations reveal? Several research directions could advance our understanding. Continued long-term radial velocity monitoring could detect additional planets in the system, improve orbital parameters through decades of observations, measure secular changes in orbital elements, and potentially detect planets at wider separations requiring longer observation baselines. High-contrast imaging from extremely large telescopes might eventually resolve 30 Arietis b as a separate point of light from the star. The planet's separation of 1.3 AU at 136 light-years corresponds to about 10 milliarc-seconds. Extremely challenging, but potentially within reach of future 30 to 40-meter telescopes with advanced adaptive optics and coronagraphs. Direct imaging would enable atmospheric spectroscopy, revealing composition, temperature, and cloud properties. Precise astrometry from missions like Gaia might detect the stellar wobble through position measurements, providing an independent mass measurement that could constrain orbital inclination and determine the true mass rather than minimum mass. Long-term photometric monitoring might detect stellar variability related to star-planet interactions or stellar evolution, providing additional constraints on stellar properties and system architecture. Even without extensive new observations, 30 Arietis b remains valuable for comparative studies analyzing populations of massive planets around evolved stars to identify statistical trends and test formation theories. Chapter 9. Conclusion. Let's recap what we've learned. 30 Arietis b is a massive gas giant discovered in 2009 through radial velocity observations, with a minimum mass of 9.88 Jupiter masses orbiting every 335 days at 1.3 astronomical units from a K1 subgiant star. The moderate orbital eccentricity of 0.289 creates varying stellar flux throughout the orbit, affecting atmospheric conditions seasonally. What makes 30 Arietis b particularly interesting is its evolved stellar host. The star has already left the main sequence and begun expanding toward becoming a red giant, fundamentally changing the planetary environment and providing a glimpse of what planetary systems experience billions of years into stellar evolution. With a mass approaching the planet-brown dwarf boundary, 30 Arietis b occupies an important parameter space, revealing the continuum between planetary and substellar objects. At 1.3 AU, similar to Earth's orbital distance, but around an evolved star, it fills the gap between hot Jupiters and distant directly imaged planets. The discovery through radial velocity demonstrates the continued value of this pioneering detection method that launched the exoplanet revolution. And remarkably, 30 Arietis is visible to the naked eye, connecting casual stargazers to this distant planetary system. 136 light-years away, 30 Arietis b continues its year-long orbit around a star slowly expanding toward red giant status. Nearly 10 times Jupiter's mass, this world experiences changing stellar flux as its moderately eccentric orbit carries it from 0.93 to 1.67 AU. Seasons driven by orbital distance, temperatures varying from 250 to 400 Kelvin, and an atmosphere dominated by hydrogen, helium, and methane characterize this massive world. Over millions of years, the star will continue expanding, increasing in luminosity, engulfing inner regions where any closer planets might once have orbited. 30 Arietis b, at 1.3 AU, will watch this evolution from what's currently a relatively safe distance, though even it might eventually be engulfed if the star becomes large enough during its red giant phase billions of years hence. The story of 30 Arietis b reminds us that planetary systems aren't static. They evolve alongside their stars over billions of years. Understanding planets around evolved stars reveals what happens to planetary systems during stellar evolution and provides a preview of our own solar system's fate when the Sun eventually leaves the main sequence billions of years from now. Every planet we discover and characterize expands our understanding of how planetary systems form, evolve, and eventually end. 30 Arietis b, massive and orbiting an aging star you can see with your naked eye, connects us to the full life cycle of planetary systems across the galaxy. What questions do you have about 30 Arietis b? How do you think massive planets like this form? What do you think will happen to 30 Arietis b as its star continues evolving? Share your thoughts in the comments. If you made it all the way through this video, thank you so much. It really does mean all the world to me. Make sure to like, subscribe, and leave a comment about what exoplanet I should cover in the next video. I'll see you tomorrow, and thank you for watching.